Ladies and gentlemen, all participants, as you are all aware, we happen to meet in a very strange time. And I don't think that just a week ago anyone could believe that we may have war in Europe. And this particularly concerns us here, as Eastern Europe, for which this seminar is intended, is directly involved. And we think about young people who, instead of fulfilling their dreams, doing work, including their beloved geomorphology, have other worries, are being killed or are sent to combat. And having all this in mind, may I therefore ask all of you, as we are here, before we start, to have a minute of silence to commemorate all victims of this madness instigated by people who think that war is the answer and solution. So please keep silent for just a while. Thank you.
Okay, thank you very much, Piotr, for the introduction. You are all welcome to our Central Eastern Europe webinar, which belongs to the International Week of Geomorphology. We are very happy and proud to have here with us the president of the International Association of Geomorphologists, Professor Mauro Soldati. Professor, the floor is yours for a short introduction. Thank you very much.
Thank you very much, Mihai. It's a great pleasure for me to be here today and talk about science, and especially geomorphology during such sad days. So I hope that you will have the chance to spend some time on and looking at landscapes, understanding their evolution, past evolution, present time evolution, and future evolution. And I hope there will be discussion on these topics during the whole webinar. This is actually the second webinar of a series of 9 regional webinars that are organized by the IEG within this third International Geomorphology Week. The first one has just started this morning, and this regarded Africa. It is ongoing. I have participated in the first hours of the webinar, and it was quite successful, I can say, as I'm sure this one will be successful. I would like to thank the chairs of this webinar, my colleagues and friends Piotr Migon, Konstantinos Vuvalidis, and Mihai Miku for organizing this event, and for all those of the executive committee of the IG who work behind the scenes, like, for example, our Vice President, Susan Conway. I see that you have a very intense program. I will have to leave and join back Africa at the end of their webinar, and then I will be back again in the afternoon. And I wish you really a pleasant day talking about geomorphology. And I just would like to let you know that you can easily access the program of the Geomorphology Week looking at, I will copy the link in a second, looking at the IG website at the address geomorph.org. So you will not only find information about the 9 official webinars promoted by the IEG, but also of very interesting side events that are taking place during the whole week, and also with an appendix next week. And I'm talking about the second workshop dedicated to women in geomorphology that will take place on the 8th of March. Finally, I would just like to invite you all to submit an abstract for the Coimbra conference, which is the international conference on geomorphology that will be held at half September in Portugal. And the deadline for submission of abstract is 14th March. And you are all welcome to do that. And hopefully we will be there in presence after the possible and the end of the pandemic. So I truly hope to see as many of you as possible in Coimbra in September. But by now, have a good meeting, and thanks to all for your participation.
Okay, so hello again. My name is Renata Feher. I'm a PhD student at the West University of Timișoara. And today I will present our newest work, let's say, the snow avalanche activity in the Țarcu Mountains. This study was coordinated by my PhD coordinator, Professor Mircea Voiculescu, and my two mentors, Patrick Chiroiu and Aurel Perșoiu. And I also want to thank Patrick for the help in the fieldwork. So, first of all, what's the reason why we choose this study area? Well, first of all, because there's no study in this area. So there are a lot of studies in the Southern Carpathians, this kind of avalanche reconstruction, but there is no study in the Țarcu Mountains. So we wanted to fill a gap in knowledge in this field. Then the purpose of this study is to highlight the avalanche activity in these mountains. About the objective, we have seen that there are several common years with major avalanche events in other mountain areas in the Southern Carpathians. For example, the year 2005, it can be found in every snow avalanche couloir in the others. So we want to see if this is happening also in the Țarcu Mountains, and to see if the events are synchronous with the others. So the study area, as I told you, is in the Țarcu Mountains, which is located in the northwestern part of the Southern Carpathians. You can see it here in the small map. And then we have our couloir here, which is near the Țarcu Meteorological Station. About the geographical position of the investigated couloir, we can see that it is near other peaks like Gugu Peak and Căleanu Peak. And here we have a map with the altitudes, which vary between less than 500 meters and more than 2,000 meters. Our couloir here, it is located between 1,400 meters and almost 2,000 meters. Here we have two pictures. The first one is made on the field last summer with our couloir, and the second one is in Google Earth, and the yellow dots represent the sampled trees. And in the small table, we can see some information about the couloir. For example, the orientation of the couloir, which is eastern, the altitude in the starting zone, which is at 1,950 meters, in the runout zone, 1,500 meters, and the altitude difference. Also the surface of the couloir and the forest vegetation with pitch abies or spruces. Now, one of the most important factors that lead to avalanche activity is the topographic factor. And here we have two maps. The first one represented the slope values of our study area, and the second one represents the slope orientation. On the first map, we can see that the slopes are between 10 and 25 degrees, not so high. And in the second map, the orientation, we can see it is northeastern and southeastern. Here we have the age of the sampled trees. The youngest tree have 9 years old, and the oldest one is 179 years old, and the average age is 38.3. I've made the age structure here in this graph, and we can see that most of the trees are between 21 and 50 years old, so they are relatively young trees. And I also made a map with the distribution of this structure, and we can observe that the youngest trees are situated in the upper part of the couloir and inside the couloir. Here we can see some pictures with the mechanical impact of avalanches on trees. So we can see the broken trees, tilted trees, and curved trees. Now, what's interesting that what we see on the outside, these anomalies, we can also find it in the tree ring. And here I've made a table with the chronological distribution of different types of anomalies. We have reaction wood, traumatic resin ducts, growth suppression, and one scar. And here we have the years when we found these reactions. Now, what's happening with this reaction wood? This reaction wood is this brown colored rings. A tree whose trunk has been tilted from a geomorphological event will try to regain its vertical position. And the result of this effort, let's say, is the curvature of the trunk. And this adaptation is possible by forming this reaction wood. Then we have, on the opposite side of the reaction wood, we have growth suppression. You can see the very narrowed tree rings, sorry. And also we can find traumatic resin ducts, which is the formation of tangential rows of traumatic resin ducts after a tree was traumatized by a geomorphological event, usually corrosion. And this response is generated by the activation of protection mechanisms through supplementary production of resin for healing and sealing somehow the wound. Here we have the snow avalanche reconstruction. Schroeder established an annual index for the event's reconstruction, which is the ratio between the trees with the growth disturbances in 1 year and the sample trees that are alive in that year. Here we have the formula, and after we apply the formula, we reconstructed some events. And with the yellow line, I put the threshold of 10%, and the red line, it's the threshold for 20%. And you can see that here we have some years who are higher than this red line: 2000, 2005, 2007, and 1982 as well. After we made this thing, we made the chronology. So after we identified these growth disturbances, we assigned an intensity class for each reaction and differentiated between weak, intermediate, or strong intensity. And we can see that the year 2007 was the, let's say, has the strongest responses. After that, we calculated the return period, or the frequency, which represent the return interval by the ratio between the age of one tree and the number of events recorded by the tree. And here I've made a table with our return period calculated for the Țarcu Mountains, and the others are from the Făgăraș Mountains and Bucegi Mountains. And you can see that our value is higher than the others. Oh. Okay, now I've made a map with this return period calculated for each tree, and I also showed them on the map here. And we can see that the periods between 4 and 10 years, maybe until 20 years, are located almost everywhere, but the periods between 40 or 50 years are located somehow on the outer part of the couloir. And in the other map here, we calculated the spatial extent of the 2005 avalanche event, and we can see that almost all the trees were affected in 2005. Now I've classified our couloir based on the return period and biopedological features by Weir in 2002. And we can see that the return period between 10 and 30 years is characterized by the predominance of pioneer species, the dense growth of small and young trees, and the affected forest at the edge of the corridor. And here we have two pictures from the field. We can see here the small trees located at the edge of the forest. And we have also found alder or Alnus viridis, the small trees. And about the synchronicity I was telling you about at the beginning of the presentation, we have found 11 events that are synchronous with events from other avalanche couloirs. 8 events that have the IT, that index between 10 and 20%, and 3 events with IT between 20 and 40%. And here we can see the year 2005, 2007, and 2000. And I've also made here, I try to represent it more clearly, let's say. We can see the 2005 everywhere, literally everywhere, in Țarcu Mountains, in Piatra Craiului Mountains, in Bucegi, Făgăraș, everywhere. So this was just the first step in this study. The conclusion for the study is that the morphology of our area is that we have constrained avalanches. We identified 51 events in a 100-year chronology in spruces. We had found 12 events with IT between 10 and 20%. And the 2005 event is synchronous with other 9 couloirs. Then we calculated the return periods, which were smaller than those obtained by Corona in 2007 in the Swiss Alps, but they are similar to those obtained by Dicol in northern Iceland. And as I told you before, 11 events synchronous with events of other 11 couloirs. And in the future, we want to see what happened in these years. What were the climatic features, let's say, the precipitation, the amount of snow, the atmospheric circulation. So this is our next step, to see what's happening in those years. Now that we filled the gap in Țarcu Mountains, we have all the mountain ranges, and this will be the next step. And my last slide, 1 second. Yes, I would just want to thank you for your attention and to thank Olympi-Pop for helping us with the sample processing. So thank you again.
So thanks for the introduction and for the opportunity to present my research from the Antarctic here at this webinar. And I'd just like to introduce you some of our findings on the dating of the really cold environments around the Antarctic Peninsula. Certainly you can imagine why it's important to study this glaciated continent, why it has ramifications for this present climate crisis on the Earth, and why it's important to know how the glaciers evolved on the long time scales, like from the last glacial maximum and during the Holocene. Also that it can contribute to the global sea level rise. And even though we have quite a good knowledge of some of the climate changes, still some local knowledge on how the specific parts of the Antarctic Peninsula ice sheet was behaving, it's still lacking. And this is just to note that really the Antarctic Peninsula is one of the most rapidly warming parts of the Earth, or at least it was in the 20th century. But it's expected to continue also in the future. This is the Mendel Station, where the Czech Antarctic Research Program is operating mainly. I think we'll have one more talk today from this area with my colleague Lenka Ondráčková, so at least you get an idea how it looks there. And just to have the, so that you know where we are, it's really at the tip of this Antarctic Peninsula on James Ross Island, and we'll be mainly looking at this area and the record of the glaciation. I'll present you two main methods how we constrained the glaciation. One is, of course, the surface exposure dating of these glacial erratics here with the colleague Michal Břežný. I'll show you some preliminary results of dating of these erratics, where you can see that if we do a probability density plot, that the deglaciation began in my areas of interest some 8,000 years ago and continued throughout the Holocene. And here on the map, you can actually see how the quite complex picture of...
Sorry, Matěj.
Yes?
Matěj, sorry. We see only the first slide of your presentation.
Really?
Since the beginning,
So-
at least myself, I'm seeing the first slide only. Now it switched to slide number 7.
Okay, that's strange. How?
So please switch to full screen presentation.
Yeah, I switched and then
Go down.
yeah. So can you see the map now actually, or?
We see slide number 7 now.
Yeah. And then when I'll go further, can you see also how the presentation is showing the arrows? And now you can see the next slide as well.
No, please click on the slides, number 8, for example.
Yeah. So I think I'll.
Now you can see it.
Yeah,
Okay,
I think I'll
thanks.
better leave it here without the full screen because I could see my presentation, but probably, obviously, you couldn't. So sorry for this. I'll just.
Thank you.
Yeah, this will be easier. So just to have an idea, we are here in this part of the Antarctic Peninsula, and these are all the available data of surface exposure, dating of the glaciation in the area, and we are contributing some new results, especially from this part of Dimitrios Island, also from Vega Island, also some new data from here nearby the Antarctic Peninsula, and we hope these new results will also contribute to dating of retreat of the ice streams which float in these glacial rocks. For example, here in the Croft Bay and Herbert Sound. And of course, it's mainly these dynamic, fast ice streams that influenced the whole deglaciation of the area. These are like the most rapid parts of the ice sheets that flowed from the centers of ice accumulation towards the continent margins. So I'm sorry you couldn't see all of the pictures, but I think I'll just move on to the next part of my presentation, which is more paleolimnological oriented. And here, this is an example of the coring of lake sediments on the Vega Island, which is where you can actually see how wonderful resolution, high resolution laminae we could obtain. This is now I will mainly speak mostly about monolith lake, which is from Dimitrios Island, where unfortunately I don't have the pictures of the coring, but this is an interesting lake from the point of view that it's in the way of where the glacier left the hyalocostite boulder train, and which also dammed the lake partly, and it's thanks to this feature that we can date the time of deglaciation in this area. You can also see it here, how the glacier left these scattered boulders in this plain. I'll just quickly show you the results of the core, which measured some 50 centimeters, and there are basically two main parts. One with with the proxy data, which are almost without any trends, and they more or less approximate the time of rapid deposition of the sediments just after the deglaciation. And then only in the topmost 10 centimeters, there is the recent period of deposition, also the organogenic deposition. This is mostly the same picture, only with geochemical proxy data. And you can also see this division into zones, into two zones via stratigraphic clustering. Or also via other statistical methods, which I think I'll not delve into more detail right now. Also, the living creatures can only be found in the topmost 10 centimeters. So they also further demonstrate that previously the sedimentation was very minerogenic and probably signaling the rapid deglaciation. We can also see it from the optically stimulated luminescence dating of the sediment, which reveals this sudden this hiatus where the sedimentation did not occur, and on the contrary, the rapid deposition, which could take place basically in a couple of years or tens of years based on the age depth model. And it also it's matching quite well with the previous work from the Swedes of Björk and others in the 90s. Also, thanks to other comparative studies from this time again surface exposure dating from the area, which is in progress from my colleague Steve Jennings, we can see the retreat pattern of this lookalike glacier from the north toward the south, and that the surface exposure ages match quite well with our OSL ages. So we've got this this independent control of the correctness of our data. And especially in the Antarctic, it's important to always have some independent control of the dating. It's also yes.
2 minutes to
Thank
go.
you. It's especially important with the paleolimnological records of deglaciation and climate evolution around the Antarctic, because as we could see in our record, there was an unexpected hiatus, which was not described previously, and so we compiled this meta-analysis of published paleolimnological records around the Antarctic, and made the analysis of how often these events are occurring around the Antarctic, and they seem to be more common than previously thought. Also, as you can see in this inset figure, which basically can show the rapid sedimentation events, or the hiatus, or for example, for example, age reversals in the sedimentary cores. And then when we made some, when we plotted on the frequency histograms, or like as kernel density, we can see that actually, especially in the last 2,000 years, there's not as many ages in the sedimentary cores from lakes as we might assume that the more recent, the more to the present, the more ages we should get. And it seems to be either climatically controlled, that during the colder neoglacial conditions, there's not as much sediment deposited as there should be, or also because the deglaciation wasn't proceeding as fast around the Antarctic. So again, there's not so many lakes forming and not enough sediment accumulated. And with that, I'd just like to thank my many colleagues, especially my supervisor, Daniel Nivel, also Neil Glasser, David Sanderson, and Regis Brauscher, where I had the opportunity to work, and all other my colleagues from the field and the lab. And thank you. If you have any questions, please ask.
Perfect. I want to invite you for a small presentation of my last year work during my PhD studies. Well, as as Professor Mihai said, that I was working on the inventory of glacial lake systems on Svalbard, and I tried to make the susceptibility for the glacial lake outburst floods, which are quite big geohazard nowadays with the climate change. So I want to make a quick introduction how it works and why I started to do this. Okay, so first of all, how it started. Well, when I wanted to go for my PhD studies, I talked with my supervisor, Mateusz Strzelecki, and he showed me an article from last year. You can see it here. It's a rapid worldwide growth of glacial lakes since 90s. And it shows how the glacial lakes around the world were growing up from the 90s, and that this trend is actually much quicker now. And when I read this article, I saw that there are 3 regions missed during this inventory, and one of these regions was Svalbard. Svalbard, you can see here. It's an archipelago which by administration belongs to Norway. And well, let's say that Svalbard is connected with the history of the polar sciences from the Poland also for many years. So it was actually quite natural to connect with my PhD with this Svalbard region. So I started to dig with the data and start to check if there is any information about glacial lakes and how they develop. And I actually get the information that because of the lack of the satellite data, nobody made this inventory of glacial lakes. So I started to dig with data, and I found some database. First of all, I started with Norwegian Polar Institute data, which you can see with this yellow bolded types. And it was aerial images from 2008-2012. And that was my baseline of whole inventory. So I started to check the glacial lakes. I did it by checking glacial lakes which have a straight connect with the glaciers during these years. And actually, I found 566 lakes like this. And from that baseline, I started to try to compare these glacial lakes with other data. As you can see, the oldest one are the aerial images from the 30s, also made by Norwegian Polar Institute. Then I've got digital data from the 90s. And then I added to this from Google Earth data. There are satellite images for 2013-2019. At the end of it, I checked the satellite images from the Sentinel for 2020. So this is the newest data for me. And I also used the archival maps and archival photographs just to make sure if there was everything correct. So I was, for the last year, I was like checking slowly every data set for this. So it took me a lot of work, but at least I managed to do so. So as my inventory looks like, it looks like this. So you can see every map for every single period, which I showed you from the last slide. And you can see that on the 30s, for the 30s, I did not get the quality data, so I just get the quantitative data. So I could say only if there was a lake, which I detected in the 2008 and 2012 as my baseline. And I put a dot if there was a lake or it wasn't. Then I did the same for the 90s, but I also add information about the area of lakes. And then for the 2013 and 2019 from the Google Earth. And at the beginning, as I said, it was from the Sentinel. So you can see that in the 30s, I just searched for the 120 lakes which have been already on the Svalbard. Then it all grows to the 314. We've got 566 lakes in the baseline period. And then I have 264 from the Google Earth satellite images. And you can see there's a lot of red dots over there because there was no data about this. So because there was no images for these places. So I added Sentinel data just to fulfill the gaps of data. And actually, I've got like a full line of inventory. And as the finish of this inventory, I made the small diagram, which shows that from the 90s till 2020, the total area of glacial lakes on Svalbard is still growing up. But I have to say that the total number of lakes, it's not growing up because a lot of lakes merge or just drainage or something like this. But the total area just grow up. It shows that the changing on the proglacial zones of the glacial lakes is very important for Svalbard landscape as for whole world. So it looks like this. I just made a little GIF to show you those changes in these years. It's in the loop, so you can just observe a little bit. And the major trend is that the glacial lakes are more and more important in glacial landscapes of Svalbard. So this is how it looks from the on the images. Okay, and some few examples just to show how they grew up. I put like through one of my best examples how they grew up. I use, of course, here satellite images mostly, and also aerial images for 3 lakes. So you can see that each of these lakes grow up in size like a lot. And there are like different type of lakes. Here you have mostly end moraine damped lakes, which are actually, of course, damped by moraine. And with showing this, I can say that there is a lot of geohazard connected with this, which I want to show you. And to show this geohazard, which is Glacial Lake Arbus Flat, I started to compare the geological data with this data, which I already made during inventory. And I saw that on the west side of the Spitsbergen, we have mostly moraine damped lakes. In the central part is mostly ice damped lakes, and on the North Auslandet Islands, so you can see it on the northeastern part of Svalbard archipelago, you can see mostly bedrock damped lakes. So if we take the look in the literature from around the world, you can say that the biggest hazards is connected with the ice damped lakes and moraine damped lakes, which are actually the biggest susceptibility for the gloves. So I started to dig it up with data and to show what is how big is this geohazard for this. And I wanted to make like a statistical approach to this. So I wanted to make how to check which lakes are considered like a geohazard. So first of all, I have to say that we've got these 3 types of glacial lakes. You can see on the left up figure, and on the right up photographs, you can see also these lakes on the Svalbard. So there's an end moraine dam, there's a bedrock damped lake, and ice damped lake. On the down right figure, you can see that there are 2 different approaches, because I showed that geohazard connected with glacial lakes Audros Flat, it would be when the difference between dam top and the glacial lake, it will be about 1 meter. But the problem which is with it is that you can take 2 dams. One is very wide on the up part of this figure, and second one on the down part of this figure is very narrow. So the
10 minutes, 2 minutes
okay.
to go.
So the down part figure is the biggest glacial lake. This is the bigger geohazard with connected with this, but it's hard to say basing only by the on the satellite images. So it needs a lot of work during fieldwork, and I hope that next season I will go for the fieldwork and have a chance to measure this kind of geohazard. So based on this, I put like suggestion where and when the geohazards could happen on the Svalbard. So basing on history data, I just showed that between two first periods, it was about 10 gloves or fast drainage lakes. Then between 90s and 28, it was 63. And between 2012 and 2020, it was about 183 glacial lakes, all fast lake drainage. It's hard to say, like I said, without any fieldworks. And also I made a potential growth events map based on the area of those lakes and the difference between dam top and the lake, like I showed on the previous slide, and it's how it looks. So you can say that in next days, it could in next years, maybe like this, it could be the geohazard of glacial lakes almost flat could be growing and growing on Svalbard. So all of these photographs, maps, etc., are from my latest work, which I just put in the Karst Fair open discussion. So I would like to invite you if you have any ideas for my work or you want to say something more, you can still put your comment in discussion till 8th of March. I would be very happy to have more comments because after the 8th of March, I'm trying to respond for all of the comments from the reviewers. So I would be very happy if someone would be interested in this. And from this, it's all of what I wanted to say you, and thank you very much for your attention. And if you have any question, I would be happy to ask for them.
Thank you very much. Thank you very much, Ivo.
My name is Mihai Radu. I'm a PhD student in Timișoara. In this presentation, I want to integrate the two areas of my study about the erosion rate along tourist trails in Southern Carpathians. As an introduction, as most of you already know, tourist trails are a network with a key role in preventing tourist dispersion and also have a role for recreation. But in the forested areas, because of the tourist impact, also by natural means like water, but under the impact of tourists, dendrogeomorphology comes and helps us investigate the erosion rate because the erosion reveals exposed roots. The aims of this study are to estimate the erosion rate along some tourist trails in Făgăraș and the Bucegi Mountains, also assess and classify the hiking trails and correlate slope and erosion. And also a bit difficult point is estimate the intensity of tourist flows because there are no real tourist data in Romania, but for this I tried to use the scars and the traumatic resin ducts present on the routes. Now I will integrate my two study areas from my PhD study. So one study area is in Bucegi Mountains, to the right, the Bucegi Mountains at the east of the Southern Carpathians. There are 3 tourist trails, but I will insist now on 2 of them. Both of them start in Sinaia Resort and go up to Hotel 1,400 meters, which is a good viewpoint for the entire area and a nice climb. The 2 trails are very close one to another. In some places just a few meters. They are almost parallel. Just that one is a hiking trail and the other is a biking trail used downhill. There's also a road and a cable car in the area, so the tourist flows on the hiking trail decreased, while since the biking trail is opened, you'll see in the results what happened. Then the other area is in Făgăraș Mountain, the most is the highest mountains in Romania. and it's along Bâlea Valley where the road called Transfăgărășan passes by. And the three investigated trails start at Bâlea Waterfall Chalet. One of them goes to the Bâlea Waterfall and back, so it's used in both ways. The other two trails climb up to the lake, one of them along Bâlea Valley, and the other goes around and goes up to through Doamnei Valley. Here you can see the forested area, so I investigated just the forested area because I concentrated on dendrogeomorphological samples. I took entire root samples, as you can see in the photo, looking for exposed roots and alive roots still alive, and which are just partly out of which are just partly out and in the trail. We took some measures in the field along the trails, and also investigated the callus tissues, the traumatic resin ducts, and the scars, also calculating the erosion rate. The samples were prepared according to standard geomorphological techniques, like dried, grinded progressively with sandpaper, and also scanned at a high resolution, then analyzed in specialized software like CDendro and Core Recorder. The estimated erosion rate was calculated taking into consideration the number of years since the exposure, the growth in the upper and lower parts, the bark thickness, and AX, which is the distance it's out of the it got out of the surface because of the erosion processes. As results, you can see here the number of scars along the trails in Bucegi Mountains, and you can see the great number of scars in the last years. And especially, which I wanted to compare here, was the hiking impact and the biking impact, because there are studies of erosion separately, but not through the dendrogeomorphological method. And the studies along biking trails are just, how to say, are more theoretical studies, and it's not a method calculating exactly the erosion rate like here. Also, in Făgăraș Mountains, we can see the same increase in scars along the trails. Scars are produced by the pass of tourists, especially. They can be produced by large animals like bears, for example, but bears don't use the trails along them. So it can be, for example, one or two scars produced by bears or animals, but it's not such a great impact to be taken into consideration. And here you also can see, because these are newer samples in Făgăraș Mountains, the decrease in scars in 2020 and 2021, which it's like the decrease of tourism also due to coronavirus. Here are in comparison the annual erosion rates on the two areas. For example, in Făgăraș Mountains on the left, you can see the BC, which is Bâlea Cascadă, Bâlea Waterfall, is the most used trail, and in both ways it has a erosion rate more than 10 millimeters per year, while the others have around 6 or 7 millimeters per year. And in Bucegi Mountains, along the hiking trail, it's along 6 millimeters per year, while in the biking trail almost quadruples. It's 24-25 millimeters per year, the median value. Also here you can see the correlation between the erosion rate and the number of years since the exposure, which is also stated by the literature, which says that younger roots tend to provide bigger erosion rates, higher erosion rates, while older roots tend to attenuate the erosion rate. So, for example, in this study, you also have to, in these types of study, you also have to try to take medium-sized roots. Now, the other part of my study is correlating the erosion rates with the tourist flows. For example, in Țarcu Mountains, I had some data from the National Statistics Institute, but this data is just about the people who stayed in Sinaia resorts. So I can just assume that some of them went to the trails, but there are no express data regarding people entering the trails. What you can see in this graphic is that so, for example, in the upper part, is the number of tourists and the number of scars. For example, 2007 and 2009.
10 minutes, 2 minutes
okay.
To go.
Okay. In 2007 and 2009 were the years when the biking trail opened. There are 2 years mentioned in the sources. So from that on, you can see that the scars increased very much along the biking trail. So it correlates my method of study with the years since the trail opened for biking and the level of impact the biking has among the trails. And in Făgăraș Mountains, the only data I have till now are just the number of tourists I counted personally during the field studies, which were about 100 Romanian tourists along the trail which goes to the waterfall, 8 Romanian tourists along the trail which goes to the lake, and 40 foreign tourists along the other trail. Some limits of the studies of my study are that there is no uniform distribution of the routes because parts of the trails are paved, and in some parts there are no exposed routes or there are dead routes, and also the difficulties of dating the scars, especially in the case of old trees. And the last problem is validating the real number of tourists or bikers along the trails, as there are no statistics. And the conclusions that the method proves to be very useful in assessing the erosion rates of the tourist trails, and the results are similar to the others obtained in different mountain areas in Europe. And also, personally, I could assess the impact of biking.
Okay, thank you very much. Hello, everybody. Let me introduce myself again. My name is Martin Kašing, and I'm from Department of Geological Engineering, VSB Technical University of Ostrava. And I would like to present you the topic called multi-approach study of pseudokarst cave within the outer Western Carpathians. This presentation actually introduces my PhD thesis, which is compilation of 3 papers focused on yet unstudied problems or issues of 3 largest pseudokarst caves within the Czech part of outer Western Carpathians. It means these are the Tîrlă cave, Kněžinská cave, and Lenka Ondráčková cave. The research of pseudokarst caves in outer Western Carpathians is considered to be an important approach for recognition of various types of slope failures, various parameters of slope failure, CG, or for instance, its internal structure, its depth, its spatial extent, structural control, or recent movement, for example. However, many features of pseudokarst caves are still neglected or poorly studied, and it was the main motivation for my study, because this can be absolutely essential for understanding of, for example, genesis of slope failures and its development. It should be important for regional geological research and mapping, or for geomorphic interpretation of our environmental reconstructions, we can say. I think it's not needed to introduce you to Carpathians too much. Maybe it's interesting to mention that based on study by Lennart and Miklin from 2017, over 130 pseudokarst caves are present in the Czech part of outer Western Carpathians. The first study deals with the complex assessment of structural controls of the Tîrlă cave, the longest crevice-type cave in Czechia. And within this study, the detailed structural analysis, including geometric and kinematic analysis of the outcrop data, 2D and 3D geoelectric survey, and radiocarbon dating of speleothems were performed. The first step lied in analysis of cave structural control by compass measurement of faults, fractures, bedding, and these kind of structures. In the figure, you can see the fresh fault-related lineations generated by recent movements recorded on bedding planes exposed in the cave. And based on these structural measurements and analysis over the whole cave, the structural map showing cave structural control was created. It means that over 1,000 compass measurements were performed, and it revealed the general structure of these north-northeast striking fissures interconnected. You can show it, these north-northeast striking fissures interconnected by two continuous east-northeast striking dextral fracture zones, and also abundant signs of recent strike slips are quite distinct structural feature of the cave. Along with GEM imaging and analysis and a detailed survey of the cave, we also performed 2D and 3D electric resistivity tomography measurements, which completed the main image of the predisposition and structural controls of the cave. These measurements also detected unknown crevices above the existing headscarp, which indicates possible retrograde evolution of the landslide. Based on radiocarbon dating performed by our colleagues from Gliwice Radiocarbon Laboratory in Poland on the stalactite quartz, the minimum age of the cave is up to 19,900 years, calibrated years before present, which is, we suppose, the oldest age detected by radiocarbon dating in the area of outer Western Carpathians so far. The second paper focuses on the investigated study of lithology, biostratigraphy, and mineralogy within the part of the Gordula Formation exposed by the Kněhyně Cave. Kněhyně Cave is the deepest cave in the Czech sector of the outer Western Carpathians. And this lithological section of the cave represented typical proximal flysch sequence characterized by alternation of the coarse-grained sandstones with thicknesses reaching over 3.5 meters and up to, we can say, approximately 6 centimeters thick aleuropellets. The mineralogical and paleontological analyses were carried out on 5 rock samples, representing the finest members of turbidite cycle. The aleuroids and pellets contained a large number of phytoclasts and deep water dinoflagellates, indicated the material redeposition by turbidity currents, and they identified dinoflagellate assemblages, which was identified by my colleague Petr Skupian from our department, maybe assigned to lower to upper Campanian transition, which corresponds to upper Cretaceous period. The third article represents the first study of ventilation within a pseudokarst cave. The main aim of this paper was to characterize the ventilation mechanism of the Lenka Ondráčková cave. It is the third biggest cave in Czech part of outer Western Carpathians. I will mention just the most important approaches of this study. For example, I have to skip the temperature monitoring. At first, the ventilation monitoring itself. This was one of the tasks in this work was to map airflow routes within the entire cave, and the ventilation pattern was observed by temperature neutral chemical trace. So you can see it on the picture. That makes the air movement visible on every single testing site. During the winter, air mass movements are detectable within almost whole the cave flange, but are fading within or with the increasing depths of the cave. In summer, all the cave parts are static except for the shallowest.
2 minutes to go.
Excuse me?
2 minutes to go.
2 minutes, okay. So during the winter, it is, or during the summer, the cave parts are static, and except for the shallowest parts of the cave, representing the vents within relaxed zones of rock massive and cracks blocked by colluvial sediments. Cave airflow monitoring was observed during 9 monitoring campaigns, approximately from 1 to 4 hours long. The cave airflow measurement, the campaigns pointed out the average velocity ranging from 0.27 to 0.61 meter per second, which is corresponding to approximately 13 to 30,000 cubic meters per day of air, which is ventilated by the cave. But this is a rather really rough estimate of the real value of ventilation. The relation between airflow inside and outside the cave was also investigated. It was quite important approach. Correlation analysis, which was analyzing many parameters have not shown any important relations. So from the field observation, it was, from the field observation, it was obvious that there is a relation between these parameters, between airflow inside and outside the cave, because large clouds of condensed moisture from the cave appeared where the external wind velocity were increased. So by this statistical analysis was proved that this relation exists. The data set of cave airflow was subdivided based on the recorded wind velocity outside the cave. There is one subset of airflow inside the cave with a non-zero airflow outside the cave, and second subset with a zero airflow outside the cave. These were tested by F-test of equality of variance, and it was proved that these differ significantly from each other. So the only one explanation is that there is a relation between these. And for modeling and prediction of cave airflow values, 3 regression models were tested, where temperature gradient as independent variable was used. In spite of the detected relationship of cave airflow and external wind velocity, it can be summarized that during the winter, the ventilation of deeper cave levels is driven by the temperature gradient. Since this quadratic model, the last one, quadratic model explained almost 80% of the analyzed airflow variability within the data set. Okay, at the end, if I can summarize it, these were 3 papers analyzing genesis and evolution. At first, genesis and evolution by structural analysis, geophysical surveying and radiocarbon dating. The second study was first ever integrated research of lithology, mineralogy, and stratigraphy of pseudokarst cave, and the third was the first ever complex research of cave ventilation of a pseudokarst cave. Thank you for your attention.
So, hello everybody, I'm Astrid, as I was presented right now. I come from the Postojna Institute, Karst Research Institute, and I will be trying to show you how and what can you learn from this interaction between the fluvial and karst geomorphological processes, because here in Slovenia we have some very beautiful sites where these two geomorphological processes kind of interact. And just a short introduction. So I'm a geologist. I did my bachelor and master's in Jurassic and Cretaceous sedimentology and stratigraphy, but now I am dealing mostly with quaternary geomorphology and sedimentology, both on the karst surface and in caves. So I'm a young researcher at my last year of my PhD in karstology, which is actually one of a kind PhD study in the world. And I will be trying to show you what can you study as a geomorphologist and a sedimentologist in this type of regions. So probably already you know where Slovenia is located. It's located in the Central Europe. And the Postojna Basin, which is an impermeable basin surrounded by karst, is located here at the western part of Slovenia, in the northwestern part of the Dendrogeomorphological mountains, where actually karst is a really important geomorphological type. So as you can see on the left picture, Postojna Basin is a basin indeed. It's with impermeable properties because it's made of Eocene fish rocks, and it's surrounded by a higher karst landscape. The Postojna Basin is around 550 meters above sea level, whether the karst surroundings is from let's say 600 up to 1,300 meters, so it's higher. However, the Postojna Basin is the youngest as per the geological point of view. Of course, the Quaternary alluvium is the youngest, but the Eocene fish is younger than all the geological surroundings, which is made mainly of Jurassic, Cretaceous limestones, limestone breccias, and of course also some Triassic dolomites. And this can be the case here because of the very complex tectonic structure of Slovenia, especially here in this part, because it is surrounded by transverse dynamic faults and also by thrusts. And of course, this basin is also a syncline. So all that makes possible that the basin is at lower altitudes than the surroundings. And because of the impermeable properties, we have a lot of streams, a lot of rivers, which are mainly sinking in the karst surroundings, making these beautiful and very important contact karst features. So as you can see on the right picture, where is the approximate border between Flysch ridges and gullies and the dolines, which they can be seen really from afar in the karst, and these elongated features are actually contact karst features, which we have plenty. So this is the my case study of the Slavinski Ravnik corrosional plain. Actually, within my PhD studies, I'm researching the whole edge, the whole contact karst edge, but today I will be focusing more on this southern part of the Slavinski Ravnik. So for those who don't know, contact karst is karst that is developed on the contact between impermeable and permeable rocks, in this case between Flysch and limestones mainly. And as Ford and Williams also said, it is a karst with allogenic input, which is very important for the preservation of these contact karst features, both surface and subsurface. And for us, it's easier to see the differences and to see these features in the surface. So we can have spring or polar contact karst features depending on if the river or the stream is sinking into the karst or if it's springing. And at our institute, we made a really important discovery just around the 1994 and 95, where my colleagues from the institute found some very special features, like you can see on these right pictures. And it was thought previously that the pre-karst phase, let's call it the pre-karst phase, it's a phase when the streams were flowing on top of the karst, when there was still Flysch rocks on top. But then after they had an extensive field work during the construction of a highway, they found in these features filled with allogenic sediments, of course, speleothems. And that, with the knowledge that the karst is constantly lowering due to denudation, actually became a very important knowledge that these were some previous caves actually denuded by the denudation and made them roofless. So this changed quite a lot the understanding of karst, and you can also see some of these features here in this geomorphological map of the Slavinski Ravnik corrosional plain, where actually a very long 4.3 kilometer long unroofed cave was also discovered. Nevertheless, we have active or relict contact karst features here, depending on whether the hydrological conditions are still here or the forms already karstified, so you don't have any more allogenic input, let's say. And sediments, which can give us also a lot of information about these geomorphological features, can be found both allogenic and also autochthonous, such as speleothems. So we know a lot of polar contact karst forms. These are just a few. We know like polar steepheads, where the stream is actually sinking in the contact between, for example, Flysch and limestone. Then you have a lot of alluviated features, which can be found. That can be blind valleys, contact karst alluvial fans, polar caves, which can be where very much alluviated, can form also paragenetic cave systems, and so on. So what can we study in contact karst if we are geomorphologists? So first, we are lucky in Slovenia, we have LiDAR imaging for free, and that can be very, very useful alongside with digital elevation models, because in these parts of Slovenia, we have a lot of trees, a lot of leaves, and actually, let's say, fieldwork can be very a hard process to learn. And of course, geological mapping, geomorphological mapping, and further on, the detailed studies of these contact karst geomorphological features can be done. So this is just an example of flooded blind valley here nearby. And if you're lucky enough, and if you have some caving gear, you can go also underground, where you can study some wall and ceiling features in caves, which can give you a lot of information about the genesis of this cave. And of course, if you connect these information with the surface information you gained, you can get a lot of information about the whole area. We have also cave register, which is really good for gaining some previous information about speleological research within caves. And of course, you can do cave mapping, studying the morphology of the whole cave, and reviewing potential sediment profiles for further analysis. This is actually what I do within my PhD. So as a sedimentologist, you can study sediments on surface, you can map them, you can drill, make some sedimentological drilling and sampling, and of course, again, a lot of petrological information. We have also some X-ray powder diffraction machine here at the Institute, so we can know more about mineralogical and also geochemical composition of these sediments. And of course, also where speleothems, stalagmites, for example, are available, they can give us a lot of information. So underground, it's let's say the environment underground is more covered. It's more let's say you don't have so much weathering or any actually as you have on the surface. So the sediments are more preserved. You can gain a lot of information with dating here, as you probably already know. So
2 minutes remaining.
Okay.
2 minutes remaining.
Yes, thank you. So we are doing paleontological analysis, paleomagnetism, uranium series, and of course, a lot of this information is used for gaining the geochronological data we need. So to conclude, what can we learn within this contact karst? We can, with the geomorphological mapping, we can learn a lot about the stages in the development of contact karst, both subsurface, of course, in caves and on surface. We can try to connect them and gain the information about the genesis of the whole study area. We can learn a lot about the provenience of the sediment and, of course, about the paleoclimate in which this sediment were eroded from the basic rocks. And with all the datings, we can connect everything to a story, which can give us information also about tectonic processes, which is the case here in Slovenia as well. So if you have any more questions, I'm happy to answer you on my email also. Thank you.
Okay, so going back to the central Southern Carpathians, where also our colleagues continue Švara work. I will present some records of the alpine karst this time, the alpine karst environment. But first, let me introduce you somehow into the global scientific context, meaning that we focused on the island type glaciated karst, which is a sensitive and complex landscape capable of preserving unique evidence of past environments in alpine caves, and their sedimentary content were our primary focus because of their particular record of the tectonics, geomorphology, climate, soil, and vegetation, of course, and some ideas that our research was based on. First, speleothems from the alpine environments are high-resolution terrestrial archives of large-scale climate dynamics, and they can show or reflect optimal environmental conditions at mid and high latitudes, which were restricted mostly to warm periods. Our quite linked to these basic findings. So the focus was on the karst landforms, the caves, very small caves, in fact, and the speleothems from the topmost level of the Southern Carpathians in relation to past glaciated landscape. Why that? Because we wanted to achieve more information about the Quaternary alpine environments and constraint for the paleoclimatic interpretation. So our objectives were firstly, to analyze the geomorphic and structural context of karst and cave development. Secondly, to find the speleothem growth range and paleoenvironment records from stable isotope analysis, mainly stable carbon isotope these times, and sediment analysis of plastic infill. Then, based on these findings, to elaborate a possible scenario on the quaternary landscape evolution of this particular place, and establish correlations with regional paleoclimatic and paleotectonic events like glaciations, glacial phases, or mountain uplift. The geographic setting and geology mainly consists, so we are here in the Făgăraș Mountains, the central part of the Făgăraș Mountains. The lithology basically consists in here in mica schist and gneiss, which is the main host rock, but these rocks have some marble stripes, which are of interest because they host this island type karst in alpine setting. So you can see here a bunch of cave entrances, truncated caves, and cave remnants, unroofed caves, even collapsed dolines, which are in fact parts of some unroofed caves, which were of primary interest for our study. The geomorphic context, so we are here at about 2,400 meters high. These are the cave entrances. The length of the caves is in fact of about tens of meters. We have here some collapsed dolines, but lower into the glacial cirque, we can find some other corners, like here, many dolines, and even corner caves, which seem to be the youngest ones. This is a southwest and south-facing glacial cirque developed mostly on impure marbles, foliated marbles. We used as the main methods and techniques, first of all, fieldwork since 2015 and still ongoing, like cave and UAV survey, geomorphological mapping, microtectonic measurements, and of course sampling. Uranium, thorium dating of speleothem calcite, stabilized top, and also marble bedrock, and both marble bedrock and speleothem calcite to be able to compare the data. Radiocarbon dating of plastic sediment, then supported by further sediment analysis like hole and grain size. And we intend to do, not published yet, but we intend to do some magnetic susceptibility and further uranium lead dating. So you'll see why. This is the geomorphological map of an area of about 1 square kilometer that we have surveyed with a UAV device. We have here karst, glacial, periglacial landforms, structural landforms, and of course gravitational landforms. Some of them, like this trench of this second, being of primary interest for further studies. These are the maps for the caves in the area, for the ridge top caves, and for the longest of these caves, which is a corner cave located right here down the glacial cirque. This one is seems to be the most recent, developed into calcite marble bands, interlayered with amphibolite bands. It has a pressure tube and breakdown morphology. Condensation corrosion seems to be the dominant process, and speleothems are lacking. Compared to the ridgetop caves and even collapse dolines. So you can see here, we named it M6 cave. This is the sixth cave in the area. And we found it by digging into a collapse doline. It hosts the oldest speleothems found in the area, and we were able to provide, based on uranium thorium dating, we were able to provide the first dates for this alpine area. This could be possibly the oldest cave remnants preserved here. See them right here to the right of the slide. Speleothem ages and growth periods correlated quite well with the main interglacial times and warm periods. So this is the oldest flowstone, and of course, due to the limits of this method, it has the highest errors, but still from the other data, we could be able to infer, and from stable carbon isotope data, we were able to infer that these flowstone and in general, flowstones here in this alpine setting grown during the warm periods, when the soil and vegetation could provide more CO2, so more carbon dioxide, and that was very useful for speleothem growth. Compared to marbles, uranium concentration was quite low. So we had there 50 to 10 parts per billion, very low. But still, this resulted in larger errors, but still we could provide these correlations. Stable isotope preliminary results provided data around the -8, 9, like -10 per mil, which
2 minutes remaining.
Okay, which indicates that these flowstones were helped to grow during the presence of plant and soil cover, specific to warm periods. Radiocarbon ages and pollen results for the moment in that collapse doline provided an age of about 3,000 BP. Based on these data, we were able to provide a reconstruction scenario. This is one possible scenario of this glacial karst evolution during the last 500 and at least 560,000 years. Our results were published in the Geomorphology journal 2 years ago, but still we have further work here in progress. We intend to increase multiprox data resolution, so to perform speleothem microstratigraphy, trace elements, stable isotope profiles, then further use series dating and paleomagnetism, to establish regional to continental scale correlation, to understand better the local environmental response to climate change from more past records in alpine speleothems and plastic deposits. Like these speleothem remains, these are not dated yet, not sampled, but they come from caves that no longer exist. These remains are found in the talus screes, in the glacial cirque, and could tell us more about the minimum age of that cave that was quite eroded. And of course, from the sedimentary infill of alpine trenches like this infill of a Țarcu, we only dig for 1 meter and 70 centimeters, and we found some preliminary radiocarbon ages at, these are not calibrated ages, but still around 10,000 years at the top, and MIS3 at least at the middle. So further work, further results could allow us to obtain an almost continuous time frame for karst and glacial geomorphology of this area. Some take-home messages instead of conclusions that karst and glacial landforms may preserve sedimentary archives. These archives are reliable chronological anchors of geomorphic processes and landform evolution at a particular place. Understanding that the positional, hence geomorphic context, is the key for interpreting the multi-proxy data, and this is the link to the paleoclimate studies, allowing to provide reliable reconstruction scenarios and projections for the future. Thanks for your attention.
Hello, everyone. My name is Dimitrios-Vasileios Batzakis. I'm a PhD candidate in Harokopia University. I'm studying tsunamis, and this is what I'm going to present to you today. The title of my presentation is Coastal Vulnerability to Tsunami, the Case of Kamari Settlement in Santorini, Greece. The outline of my presentation consists of an introduction about tsunamis and their characteristics, the tectonic setting of Greece, and a short review about past tsunami in Greece. The methodology concerns the tsunami simulation and the human and building vulnerability assessment through an analytical modeling, which is the purpose of the study. The results and the summary follow. A few words about the tsunami as a hazard. It is a secondary hazard that can be triggered by submarine earthquakes, volcanic activity, and submarine or onshore landslides. Tsunamis can travel long distances and can potentially affect any coastal area in either developed or developing communities, as the recent events in the Indian Ocean and Japan showed us. Of course, it is important to study past events of tsunamis so we can prepare our communities for the future ones. And on the picture presents some critical characteristics of the hazard, which can be observed on the coastal area, and these are the inundation distance, the flow depth, the tsunami wave height, which is measured from the sea level, and the run-up, which expresses the elevation in which the flows can reach. Here is a simplified map of the tectonic setting of Greece, which is the explanation of why we have tsunamis in Greek seas. The black line represents the Hellenic subduction zone, where the African plate subducts beneath the Eurasian plate, part of which is the microplate of Aegean. The red arrow indicates the direction of this subduction that has an annual rate of 36 millimeters per year. The orange arrows indicate the areas of compression here near the plate boundary, and the areas of extension that starts from the Corinth Gulf and extends to the South Aegean Sea, where some significant extensional faults appear. In the north, we have the North Anatolian faults, which are a strike-slip fault system, which is the transform boundary between the Eurasian and Anatolian plates. and the red dots indicate the volcanic centers of the volcanic arc. All these features I described in brief make Greece one of the most tectonically active areas around the world and are linked with the appearance of tsunamis in the past. As for the potential, the Corinth Gulf is characterized as having very high potential, the eastern and western part of the Hellenic Arc with high potential, the south and east Aegean Sea with an intermediate potential, and the North Aegean Sea as low. This map, which is an online tsunami catalog, presents the sources of past events in Greek seas, and the table below lists the most significant of these events. As we see, the causes of these tsunamis are the volcanic activity, the submarine landslides, and of course, the big earthquakes that happened on the subduction zone. All these events scored the highest intensity in the 6th grade scale of Simberg Ambrasis, and 9 to 11 in the 12th grade scale of Papadopoulos Imamura. Now, moving on to the methodology, to perform the tsunami simulation, the Comet software, which is designed by the American NOAA, was used. Out of all the earthquake-triggered events from the previous slide, and according to the simulation, the one that seems to have the strongest impact in Santorini is the 365 AD event. On the bottom left of the screen, you can see the parameters of the seismic source. According to Papadimitriou and Karakostas, the length of the fault was 160 kilometers, the width 80 kilometers, the depth of the seismic epicenter 10 kilometers, and the average slip of the rupture is 8.9, and the estimated moment magnitude is 8.4, which makes it a rare mega event. The four maps above are snapshots of the wave propagation in 2, 30, 49, and 60 minutes after the seismic event. On the bottom right of the screen, you can see the time series of the wave amplitude in centimeters with respect to the time since the seismic event. And as the arrow indicates, it refers to the point near the coastline of the study area where the wave breaks. The simulation showed that the first wave arrives at about 46 minutes after the earthquake with an amplitude of 1 meter, while the second and biggest wave with an amplitude of about 4 minutes arrive 1 hour after. This map shows the overlaying of the inundation results in a high resolution DEM. A total area of 6.8 square kilometers is expected to be flooded, which is shown in blue. Also, the central and southern coast of the eastern part of the islands are the ones that expected to be the most affected. The maximum run-up is estimated to be about 10 meters, and about the inundation distance in Kamari, which is the study area, is 493 meters. The mean flow depth is 4.6, while in Perissa, another important settlement, is 5.7. And this difference in the values is due to the coastal slope that seems to be the main factor that influences the inundation. Focusing more on Kamari, the left map shows the values of the inundation distance, and on the right map, you can see the inundation with respect to the flow depth. Over here, on the left, we see the flood flow velocity calculated by using a formula that links the velocity with the flow depth. The highest values appears in the coastal front, which are about 20 meters per second, while the velocity decreases as we go inland. By using these velocity values, we have the map on the right, which shows that the coastal zone is expected to be fully flooded in about 1 minute and 20 seconds. This slide presents some calculations about the human aspects of vulnerability. On the left, the map shows the distance by which someone will need to escape the flood flows, so to be in a safe area outside the inundation. The red color presents the highest values of escape distance for someone near the coast who needs to run about 400 to 500 meters to reach a safe area. The map on the right shows the escape time. The equation of motion was used along with the value of 2.8 meters per second, which, according to the literature, is the speed a healthy adult could jog. So the results indicate that the maximum escape,
2 more minutes.
Escape time is between 2 and 3 minutes for someone who is in the red colored area of the map. The next step in the study was the building vulnerability assessment. For this reason, the fourth version of PTVA analytical model was used, where the initials mean tsunami, Papathoma tsunami vulnerability assessment. Here, this slide presents the model framework. All these components have been calculated by using a GIS software, and the equations that you can see on the screen use weights which came from the analytic hierarchy process, the AHP. So according to this model, various factors that influencing the vulnerability of the building are taken into account, such as the structural vulnerability, the exposure, the surrounding characteristics, and the water inundation data. And the final results here, as you can see on the bottom right of the screen, which are the RVI, the relative vulnerability index, are grouped into five classes. This slide presents the results of the PTVA model. In total, 423 buildings were found to be within the inundation zone. The table shows the degree of vulnerability of the building vulnerability with respect to the flow depth. And on the map, we can see that the spatial distribution of the building, and it is clear from the map that the vulnerability degree presents a linear pattern. The buildings with high and very high vulnerability are mostly in the coastal front and are near the coastline. And the further we are from the coastline, the lower the vulnerability. In general, we can say that the main factors that influence this high degree of vulnerability are mainly the low height of the buildings, the existence of basements, and of course the fact that there is no actual protection from tsunamis waves such as sea walls. The results of the model show that 58% of the buildings have high and very high vulnerability, 22 average, and 20 have minor and moderate vulnerability. The chart on the right depicts the building vulnerability level in relation to the inundation depth. The value 10 in the beginning of the horizontal axis represents the coastline, and the value 1 on the right represents the limit of the inundation zone. By reading this chart, we see that the very high vulnerability class appears to have a maximum in 8 minutes or 8 meters of the flow depth, while the high vulnerability class appears to have 2 local maxima in 8 and 7. The other vulnerability classes appears to have their local maxima in a higher elevation, more inland and further from the coastline. In summary, we can say that Greek seas are prone to tsunamis because of the tectonic setting of the area. Tsunami simulation can reveal the characteristics of the tsunami propagation and the inundation in the coastal area, not only for the past events, but also for the future, the possible future ones. Regarding the study area, the time of wave arrival and the escape time showed us that there is enough time for evacuation and that the establishment of an early warning system will be absolutely valuable. And the building vulnerability assessment revealed that there is an increased level of vulnerability, which is likely to contribute to the loss of the local comparative advantage of Kamari, which is mainly the buildings that host touristic facilities. And all this can lead to a decline in tourism development and the need to absorb financial resources for restoration and recovery. Of course, further research on how to make the settlement more resilient is needed. Thank you.
Good afternoon, everybody. I am Anna Karkani, and I will, in my presentation, I will focus on two characteristic case studies from the Aegean Sea and discuss about relative sea level changes and coastal evolution based on data we have collected from the coastal and shallow submarine environment. So we start with the first case study, which is located in the first case study are Paros and Naxos Island. They are located in the central Cyclades, just in the center of the Aegean Sea. As you can also see from the map on the right, the central Aegean is generally characterized by a relatively weak tectonic activity and the absence of large earthquakes. And regarding the Cycladic islands, they are generally considered to be affected by subsidence, which is attributed to the crustal thinning due to an extensional tectonic regime. So this case study is actually a compilation of research that has been undertaken by our team in the last years, investigating relative sea level changes in coastal evolution. So we study beach rocks found down to a depth of about 6 meters. And the data from the beach rocks are combined with sediment corings, with tidal notches, and also with archaeological data in order to assess the relative sea level changes. And these data are also compared with predictions from 2 glacial isostatic adjustment models in order to be able to evaluate the tectonic component of the relative sea level changes observed. So in the study area in both islands, we have identified 9 beach rock sites which were mapped and investigated. The majority of the sites are actually found on Naxos Island, as you can also see from the map. And in fact, the western coast of Naxos host multiple extensive submerged beach rock slabs, as we can also see from the middle of the photos in the slide. So for the study of the beach rocks, we performed a detailed spatial mapping of the submerged beach rock slabs through underwater geomorphological mapping, and also by using a UAV. We collected samples from all the beach rock sites in order to examine the cement, and also for luminescence dating. So thin sections were examined in order to determine the type of cement, and 7 samples were also dated by using OSL and IRSL. So all the dated beach rock samples from both islands show the clear intertidal formations that they were formed in the intertidal zone based on their cement characteristics, and they were transformed into relative sea level index point with an indicative range between the mean high tide and the mean low tide. Here you can see a characteristic aerial view of the submerged slabs at the western coast of Naxos. On average, we can identify 3 or 4 slabs reaching a depth of about 6.5 meters below sea level. And In fact, the beach rock submarine configuration in both islands has also provided insights into the paleogeography of the coastal zone. The site presented in this slide is very representative and appears to have well recorded the morphological configuration of the coastline in the last 4,500 years. The site is Plaka. It's located on the western coast of Naxos, and we can see from the satellite image that the submerged beach rocks can be followed parallel to the modern coast for more than 2 kilometers. We can identify 3 paleoshore lines highlighted by the yellow lines, which appear similar to the geometric shape of the modern coastline. However, if we look to the north part of the study area, we can see that the shoreline morphology recorded by the beach rock appears rather different. The orientation of the paleoshore line is not parallel to the modern coast, but appears to end up to a shallow outcrop of granodiorite, which is highlighted by the yellow circle. And this morphological configuration indicates that the geomorphology of the coastal area was different, with the presence of the paleotombolo and perhaps the existence of 2 bays due to the presence of this granodioritic outcrop. So for the reconstruction of the relative sea level changes, we also studied a series of corings that has been accomplished by our teams in both islands. The data from these sediment corings were also used to deduce relative sea level index points. And we attributed an indicative range between 0 and -2 meters for samples that were deposited in an open or marine influenced lagoon, and an indicative range between 0 and -1 for inner or semi-enclosed lagoons, sediments, samples that were deposited in such environments. Last but not least, another coastal landform that provides evidence for relative sea level changes in Paros and Naxos Islands are tidal notches. Previous underwater geomorphological surveys in central Cyclades showed that there are evidence of multiple submerged tidal notches in the area, and at least 7 former shorelines were identified that reach depths of about 2.8 meters. So these data reveal that rapid subsidence events have taken place in these islands, probably of seismic origin. So we move to this summary slide. You can see here a summary plot of the relative sea level changes that have derived from the beach rocks, from the corings, and from also archaeological data from the 2 islands. We can see that overall, the compilation of data show a relative sea level rise by 2 meters in the last 2,000 years, and by at least 3.9 meters since 4,500 years before present. And we can see in the slide, in the plot, that in comparison with the modeled curves that derive from the 2 glacial static adjustment models, our index points have a lower position. So based on the mismatch between the models and the observations for the study area, we calculate the average rates of tectonic subsidence for 3 different time frames. And we can see in general that our findings suggest an average tectonic subsidence rate close to 1 millimeter per year since 5,500 years before present. However, these rates do not appear constant during the late Holocene. And overall, we can say that the subsidence trend in the study area is actually a combination of seismic events, as indicated by the tidal notches, and a gradual long-term subsidence due to the tectonic regime that is present in the central Cyclades. We go now to the second case study. We go to Samos Island, which is located in the mid-eastern Aegean Sea. In comparison to the first case study, the island is actually characterized by a more complex relative sea level history. If we look at the northwestern coasts of the island, we find evidence of late Holocene uplift in the form of uplifted tidal notches, of benches and biological indicators. And if we look at the southeastern coasts, subsidence has been noted based on the presence of submerged geological, geomorphological, and archaeological indicators. So a bit more than a year ago, in October of 2020, an earthquake with a magnitude of about 7 took place just on the north, just north of the coast of Samos. You can see the location of the earthquake on the map. And our research actually aimed to re-examine the various sea level indicators found on the coasts of Samos by comparing past measurements with new measurements in order to quantify the ecoseismic movements that were caused by this recent seismic event. So our team did extensive fieldwork in 2015, and we visited the same sites again in 2020 after the earthquake, where we remapped the locations where we originally mapped in 2015. And we also mapped additional sites around the island in order to document the possible vertical changes after the earthquake of 2020. So we moved to this summary map with our findings from this research. You can see we can see that the northwest part of Samos has been ecoseismically uplifted by 20 to 35 centimeters after the earthquake of 2020. And you can see an example of this uplift on the sketch on the top of the slide. And if we have a look at the southeastern part of the island, actually the re-examination of the same submerged tidal notches in 2020 revealed that although they have been uplifted during the earthquake of 2020, they remained drowned. You can see this an example of this on the sketch on the bottom of the slide. So to sum up, our findings show that the island has been ecoseismically uplifted, but with different magnitude. The largest uplift is noted on the north part of Samos, with the highest values on the northwestern tip of the island. And we can also say that although the south part of the island has experienced many submergence events in the past, during this recent earthquake, it has been uplifted by up to 23 centimeters, while we can also see that this uplift fades towards the east to northeast of the island. So thank you very much for your attention.
Okay, hello everybody. My name is Apostolia Komi. I am a geologist with a master's degree in oceanography and management of the marine environment. I will present you my study with a title Coastal Vulnerability Assessment of Ios Island in Cyclades, Greece. One of the most important applied problems in coastal geomorphology today is the physical response of the coastline to sea level rise. The aim of this study is the classification of the coastal zone of Ios Island with respect to its vulnerability to the anticipated future sea level rise. For this purpose, the Coastal Vulnerability Index, known as CVI, was applied. Ios is one of the southernmost islands in Cyclades, located in central part of the Aegean Sea. The area of the island is about 105 square kilometers, with a coastline length of 110 kilometers. The island has an elongated shape with a direction northwest-southeast. Coastal vulnerability index is a simple method to estimate the vulnerability to erosion of any coastal zone in relation to the future sea level rise, and identifies areas that are comparatively more vulnerable to sea level changes. It takes into account 6 variables that are divided in 2 categories, the geological variables and the physical variables. The geological variables are geomorphology, coastal slope, and shoreline displacement, while the physical variables are relative sea level change, mean tide rates, and mean wave height. Data resources used for the present study includes topographic diagrams, orthomaps, and literature research. For the post-processing of the data, ArcMap software was used, and also the SAS digital shoreline analysis system. Each variable is ranked into 5 categories, from 1 very low to 5 very high, to highlight the different levels of vulnerability based on the available data of each variable and the ranges as proposed by the literature and as you can see in the table. Once the vulnerability is determined, the CVI is calculated as the square root of the product of the ranking variables divided by their total number. Now let's start with the results for the vulnerability ranking of the geological variables. Data concerning the geomorphology variable were derived from orthomap of 2010 by the National Cadastre. After the digitization of the coastal geomorphs, the index was applied. Most of the coastal zone of EOS, almost 93%, consists of rocky coasts and cliffs and is characterized by very low vulnerability. The next percentage of the total length of the coastline, 5.13%, consists of sandy and pocket beaches, which are characterized by very high vulnerability. As you can see in the map, very low vulnerability is characterized by green color and very high vulnerability by red color. The regional slope of the coastal zone was calculated using a digital elevation model of the area, created from topographic diagrams at the scale of 1/5000 with 4-meter contour interval, obtained from the Hellenic Military Geographical Service. The 95% of the total length of the coastline is characterized by very low vulnerability due to the presence of steep rocky cliffs with slopes over 12%. As shown by the map, areas with coastal slopes lower than 3% are characterized by very high vulnerability, and they are represented mainly by beaches and estuaries. For the calculation of the displacement rate, either there is accretion or erosion of the coastline. The coastline of EOS for the years 2010 and 1996 was digitized from orthomaps of the National Cadastre. Through the DISAS tool, it appears that most of the coastline is characterized by a rate of minus 0.1 to 0.13 meters per year, while the range of the total range of the displacement rate varies between minus 0.97 to 0.6 meters per year. In order to rank the vulnerability, the proposed by the literature ranges were taken into account. Therefore, the displacement rate for the whole coastline of Ios Island is in the category of moderate vulnerability. Now, these are the results for the vulnerability ranking of the physical variables. In order to rank the relative sea level change, two of the scenarios of the IPCC 2009 report were taken into account. These scenarios predict a rise of the sea level by 4.3 millimeters per year and 8.4 millimeters per year, respectively, for the next 100 years. So the entire coastline is characterized by very high vulnerability. According to the Hellenic Navy Hydrographic Service, the average tidal range is 14 centimeters and was considered the same along the entire coastline. Therefore, the entire coastline of Ios falls into the category of very high vulnerability. The mean annual significant wave height that appears in the area, according to the Wave and Wind Atlas of the Hellenic Seas, of the Hellenic Center of Marine Research, is 0.7 to 0.8 meters. Therefore, the entire coastline of Ios falls into the category of low vulnerability. After the ranking of each variable, the mathematical calculation of the CVI was followed. Values range from 5 to 25. The 92.37% of the total length of the coastline is characterized by very low vulnerability and occurs almost along the entire length of the coastal zone, as it consists of rocky cliff shores. The smallest percentage of the total length of the coastline of Ios is characterized by very high vulnerability and corresponds to 1.72 kilometers, which is represented by sandy beaches and pocket beaches. The conclusions conducted from the implementation of CVI show that the vulnerability of the coast to sea level rise is spatially non-uniform because of variation in some of the incorporated variables. Thus, the variables introducing the greatest variability to the CVI values are those of coastal geomorphology and the regional coastal slope. On the contrary, the other variables do not play a significant role in the differentiation of the index, having the same values for the entire coastline. So, based on these variables, over the 90% of the total length of the coastline
2 more minutes.
is characterized by very low vulnerability, as it consists of rocky shores and steep slopes. The shoreline displacement rate characterizes the coastline with moderate vulnerability based on the literature for the period of 14 years from 1996 to 2010. However, the displacement mainly concerns low-lying areas such as sandy and pocket beaches, where the regime of erosion is prevailing. These areas show very high vulnerability to future sea level rise, in contrast to the rocky shores, where their displacement is almost zero. And thank you for your attention.
I'll divide my presentation into 5 parts. I'm going to talk about research area, methods, and morphologic genetic types of coastal morphodynamics, and in conclusion, I talk about coastal development opportunities. Where is the meaning of morphodynamics? It is a special term which denotes the study of the spatial temporal changes of the coastal view. The photos show how Zelenogradsk city beach in Kaliningrad region has eroded in 3 years. This problem is very important for people living near shore, seashore. Analysis of the coastal morphodynamics gives a real focus of coastline changes for 100 years. My specific work concerns coastal research of South Kuril Islands, such as Iturup. Soviet researchers investigate this island in 1960s, but detailed maps coasts were not created. Today we can do this with the help of modern high precision methods. Due to the development of these islands, it's necessary to find coastal areas that are most suitable for pertinent constructions. Therefore, the aim of my work is to analyze coastal morphodynamics for economic development. Iturup Island is located in the south part of the Great Kuril volcanic ridge, part of Pacific Ring of Fire. It consists of several massifs and mountain ranges connected by isthmuses. There are 20 volcanoes on the island, 9 of which are active. It is the largest island of Kuril archipelago. Climate is maritime, temperate with monsoons. The weather changes several times a day. Island is too difficult to pass because of bamboo, dwarf pine, and bears. At the base of the island are volcanogenic sedimentary rocks of the middle Miocene Pliocene, represented by andesites, basalts, tuffs, and sandstones. Quaternary formations overlap them and are represented by effusives, pyroclastics, as well as preluvial, alluvial, and marine deposits. There are 3 types of relief widespread of island. Volcanic, represented by stratovolcanoes, volcanic ridges, and lava plateaus. Inundation volcanic relief of full disk of volcanoes and ridges, and coastal marine relief and terraces to which the authors focused. The main role in the development of coastal of Iturup Island belongs to the work of waves, but a number of other conditions or factors also have a significant impact of the coastal morphology and its dynamics. The active tectonic regime, the high seismicity of territory, the structural containment and geology and geomorphology structure of the coast, the extraordinary physical and geographical condition of the region, as well as specificity of non-wave relief forming processes inflow into the coastal zone of volcanic material, and tsunami threat exists. Let's talk about research methods. I took part into the expedition to Kuril Island with Russian Geographical Society in 2019 and last year. In my research, I employed several methods such as coastal observations, geomorphological descriptions, profiling, analysis of multi-temporal satellite images, and grain size analysis in faculty laboratory. Let's move on to morphogenetic types of coast. The length of coastline of the island is about 90 kilometers. 6 morphogenetic types of coasts have been identified within the island. The diagram shows that 85% of coast have as erosion appearance as a result of the tectonic uplift of these islands. Let us consider 2 distinguished types of coasts in more detail. The first type is erosion coast with active steep up to vertical cliffs worked out in effusive rocks and pyroclastics. It's occupy 31% of all coasts divided into subtypes, worked in effusive rocks and lithified pyroclastics, and worked out in unconsolidated pyroclastic. The first subtype has two varieties. The first variety with narrow surface, narrow bench and underwater bench. The cliff is composed of basaltic andesites with large columnar jointing and is covered from above the soil pyroclastic deposits. The second variety of this coast type with wide surface and underwater benches. Rich bench with erosion remnant. It is clearly that the coasts of the first subtype are most resistant to wave action. However, they are a little use for development due to the high amplitudes and steepness of the cliff. Let's move on to the second subtype. This is erosion coast with active cliff, steep cliff, walked in unconsolidated pyroclastic. Gravel pebble beaches leaning against to the cliff do not protect it from storm erosion. Slope and erosion processes are constantly going to these cliffs. The second type is erosion steep coasts with steep slopes walked out in effusive rocks and lithified pyroclastic. The marine genesis of the terraces is evidenced by the presence of rounded boulders on their surface. The first type is low erosion coasts without cliffs, with benches outside in the wave action walked out into the effusive rocks. The bench is partially covered by boulder block pavement. The fourth type is erosion denudation coasts with dying cliff walked out in effusive rock and lithified pyroclastic. There are the most common coasts of the island, according for 45%. They are divided into two subtypes. Subtype 1 is armored with landslide scree trails and boulder block pavement, which serve a natural coastal protection platform. The coastal type is resistant to wave action. They can be actively eroded only then exposed to storms and tsunami waves. Subtypes 2 is erosion denudation coasts with dying cliffs armored with large block seismic alluvium. They formed at the foot of high lava ledges and experienced a seismogenic phenomenon, absolutely not suitable for the construction of berthing facilities. Next type is accumulative coasts with full profile sand to pebble beaches. Behind the beaches are usually a series of coastal ridges. The last one is type of
2 more minutes.
Anthropogenic made of tectonic coasts in the area of point at which factories. All types of coasts are shown on the map. Let's move to coastal morphodynamics. You can see a stable coast. It's coast with high cliffs with effusive rocks, and these are stable. The decreasing coasts, it is coasts with cliff in unconsolidated pyroclastic, and increasing coasts in large bays and gulfs. But this is not stable coast, differ from those listed both in that they experience allow moving forward, taking into account several precise periods of retreat. So their final increase about 20-30 meters over 40 years. And they mainly located in open Pacific coasts. And you can see the map of morphodynamics, these coasts, and you can see different coastal areas favorable for development. And this is the one of that coast in central part of Kasatka Bay. And this is most favorable part of coast for the constructions of earthing facilities. That is conclusions, and this is the main researches, references of my research. Thank you about your attention.
Okay, so again, good afternoon to everyone. My name is Peter Labaš. I'm a PhD student at Slovak Academy of Science, Bratislava in Slovakia, and the topic of my research is the morphological development of benches on braided rivers on the Bela River case study, Slovak Carpathians. So the study area, the localization of the river is in north part of the Slovakia. It's braided wandering river with length 23.6 kilometers. It represents only 0.2% of whole river system in Slovakia. Average annual discharge in the river is 3.5 cubic meter per second in Podbanske, in north part of the river, and 6.8 on the lower part of the river. So, how I said, these annual discharges are quite small. However, the extreme flood events mostly affected the morphology of the river pattern. In the past, these extreme flood events were pretty common. However, in last decades, they are decreasing, and they are decreasing. So the river pattern is changing. As you can see in this graph, in 1949, the river pattern were mostly braided, but it's transforming because of this discharge missing into wandering and single thread river system. However, I focus on not on a river channel, but on floodplain. So floodplain in braided rivers are developed by, on the one side by eroded, and on the other side they are developed of this floodplain, developing of this floodplain. And because of the incision of the Bela River, this old major floodplain is preserved on the side of the channels. So we can study benches on this old major floodplain. Benches are unstable sediment storages. They consist mostly from sand, and they are formed by flood events, but also they are destroying but another extreme flood events that consist mostly from sand, how I said. However, the floodplain consists from gravel and from cluster. We call these preserved benches paleo benches. We create this word because of this problematic in this river. Benches has been studied mostly in Australia and North America river, and the study of these benches is missing in the Europe. and also in Central Europe. In Bela River, we found benches on 3 localizations. On localization number 1, we found active benches. How about on locality number 2 and number 3, we found these paleo benches. So this is how paleo benches looks like. It's a test pit on the bank of the inactive river channel. It consists mostly from sand, and the bottom of these paleo benches consists only from gravel and cluster, but you cannot see this because of the sand. So some results. This is locality number 2. We create these figures and this graph using DTM. We create DTM from LiDAR data, and we edit there some information from GPS measurements, from terrain survey. We create 3 real profile in this locality. We identify 2 levels of active and inactive river channels, and as you can see, they are on different elevation than the main river channel. Also, we identify 3 floodplain levels, and on these floodplain levels, we identify paleo benches. The Bela River is losing connection with this floodplain, and it has some terrace character. So this is paleo bench. They look like this. They have a thin layer of humus on top. The thickness of this humus is from 3 to 7 centimeters. These paleo benches are composed mostly by sand, but there are also some remnant of clay. We distinguish these layers in paleo benches because of the color differences. For now, we have some conclusion. First, benches are presented also in mountain streams because in previous researches, benches had been localized only in sandy and meandric stream, mostly in America and Australia. Also, we create new term paleo bench. It's intact bench with no connection to main active river zone. And the active river zone of the Bela River could keep losing connection with floodplain, and terrace character is developed. This is some hypothetical development of the river floodplain. It's a model situation. There are 3 situations, A, B, and C. In situation A, it's original braided river system of the Bela River. There were a lot of active river channels, a lot of bars, and poorly developed floodplain. However, because of the lateral shifting, simplifying, and incision of the river, the system transformed from this braided to braided wandering river system, and floodplain start developed. And in situation C, you can see some of these floodplain levels are completely developed. This active river zone is simplified. There is huge incision, and there is no room for another floodplain developing. However, the ledges appear, and ledges are a result of the extreme flood events. We localize ledges also on the Bela River. There is a lot of work in this research. We have some aims on the next research. First, we try to divide it floodplain into segments by some attributes like slope, width of the floodplain, index of migration of the river, age of floodplain. Then we try to identify benches and paleo benches on these segments. We determine the stratigraphy of every of these paleo benches, and then we try using dating of these layers using lead and cesium, and then we use also grain size analysis of paleo benches. Then we create cross-section profile of floodplain and active river section. We try to capture their benches and also paleo benches. And with this data, we try to create a process-oriented hypothesis of lateral and vertical development of the river floodplain. Also, we have some research questions. So first, what is the process of the floodplain development of the braided wandering Bela River? How many floodplain levels is possible to identify? What is the function of benches on mountain stream, and what is the potential of benches utilization of floodplain research? So this is all from my side. If you have any question, you can ask me now, or you can write me on these emails below. Thank you very much.
Okay, so good afternoon, everyone. My name is Joanna Martewicz. I'm from Poland, and I'm the last year geomorphology master student in Faculty of Earth Sciences and Spatial Management in Nicolaus Copernicus University in Toruń. It's my pleasure to participate in this webinar with my presentation about beach sediments from southern and eastern Baltic Sea. Today, I would like to present the results of my research that has been recently submitted with cooperation with my research supervisor Edyta Kelińska and Piotr Wekwert. I explored 4 sites in 2 locations, in Poland, in Stegna and Gdynia Orłowo, and in central Latvia, in Apšuciems and Lacupit. Both of them locate in the semi-closed gulfs and have quite similar geomorphology and geology. Okay. If it goes to the Polish coast, Polish site in Stegna, this is a white sandy beach. Occurs here that borders with the large dune here, with up to 25 meters. And numerous parallel beach ridges. 10 sediment were taken from this beach, were picked up here as starting from the beach ridge to the surf zone. This is beach ridge, dry beach, berm, slope of berm, wet beach and waves. So another site on the Polish coast is Gdynia Orłowo. This site differs greatly from the Stegna beach, primarily because of the close proximity of the Gdynia Orłowo cliff. You can see in this photo, most built of glacial sediment, and also it's a place popular with tourists. You can also see tourists in this photo. Samples were taken from 5 locations. It's also dry part, berm, slope of berm, wet part, and waves. Okay, Now I will give you an introduction to the location of the Latvian samples. 3 samples were taken from the beach. The wet part, berm, and the dry part, and the other 4 sites, location in the beach reach in Latupit. And the map showing the morphology of this area. We can see storm dikes and small dunes. Okay, so let's move on the method. On the slide, we see the 6 main steps to get my research aids. The first step, of course, was field sampling, but in the lab, I talking about steps in lab. Step 1 is drying samples. Step 2, sieving samples on the sieve shaker. Step 3, preparation in HCl fraction 0.5 to 0.8 millimeters. This fraction we use to Kaye analysis under a binocular microscope. The Kaye analysis determining the classes of grain roundness and type of transportation. Step 4 is a Kaye analysis under a binocular microscope. With this method, we know the sedimentation environment and transport. I'm also used the crumb-based method of grains turning. Okay, step 5 was to use CamSizer M1 device visible on this picture, which counts many parameters of individual grains. We prioritized sphericity, but I will talk about this and one moment. Okay, so let's move on the results and my interpretation. Since the first step was to sieve the samples, the obtained results of grain stains are presented first in 2 graphs. The standard deviation is a sorting, and the main grain diameter are compared. The first graph. The mean grain size reveal a wide range of values between 3.13 and minus 1.31 phi, with sample 2.1 with the finest, and sample 2.15 being the coarse. Sample 2.15 stands out in this graph with it's poorly sorted. Standard deviation is assorted, and highly mixed grains. Also mixed sediments from medium sand to fine gravel. These values show the dynamic environment conditions in the wave zone and the Gdynia-Orłowo site. The graph below compares the sorting with the skews, is the graph 2. The skews is the range of 0.5, minus 0.5 to 0.5. The relatively good sorting for all samples, and the skews values on samples, positive or negative, speaks for erosion, redeposition, or for accumulation. On the next slide, we see a graph showing the results of KE analysis for all samples, Stegna, Gdynia, Orłowo, and the Latvian coast, Apshut, Siems, and Latupit. Among all samples, the predominant grains are cracked grains and shiny, well-rounded grains. This shows a high marine energy environment, and the cracked grains also show evidence of storm records, storm episodes. Sample 2.7, it's from Stegna, and it's from Berm part in beach, stands out from the other samples. 70% of the grains are cracked grains. Aeolian mud grains also represent a small group in the samples, especially in the Gdynia Orłowo. It's because the location Gdynia Orłowo is related to human aeration, and all type of grains is so mixed. And the Latvian grains show similarities to the grains from Stegna. They are very rounded and shiny, and also often cracked. Okay, let's move on to sphericity. Note the difference between the roundness of a grain and its sphericity. Roundness refers to the edges and corners of the grain. Sphericity, on the other hand, refers to the tendency of a grain to transform into a sphere. This means that the grain can be rounded with high sphericity, but it also means that a grain can be well rounded with low sphericity. In the graph, sphericity values are shifted towards 1 with Stegna and Gdynia Orłowo, but in the Latvian side, in Latvian grains are the less spherical, but in KE analysis they are very rounded. This combination are used for grain inheritance from other environments than long sediment transport. Let's go to a biplot about sphericity. Based on the sphericity values of the individual samples and statistical approach, we created something like textural code that tells you of the length of transport and the processes involved on each group. Please take a look on the table and on the interpretation. We implemented the letter code where A letter is about the less spherical grains, and the F letter means grains with the highest sphericity. The first letter of this code tells about the dominance of more than 13% of the grains for a given graph. The second more 25%. The third letter more than 17%. The letters in parentheses represent a slight admixture of 2 to 15 grains. Each graph of grains has a statistically defined sphericity. The highest sphericity is marked with the F letter, and its values are close to 1. Sphere shape is 1. Let's look at the graphs. Most samples are in the FID graph, which the graph where 40% are grains with the highest sphericity. These grains apply mainly to the Stegna side. Going forward, the next graphs of grains have smaller and smaller sphericity, and finally, this graph, there are grains from the Latvian coast, this is evidence of storms, but also the grains were subjected to multiply reworking and previously mentioned. So let's move to the conclusions. I would like to give some conclusions that we are able to be formulated through the research. More than 50% in KE analysis tells about storms episodes. Latvian and Polish sediments from Stegna are similar in shape and texture to the KE analysis. Sphericity below 0.8 is indicative of storms, mainly in the Latvian sites. Highest sphericity of grains from 0.9228 tells about long transported, homogeneous and mature sediment. And the sphericity-based textural coding is helpful in determining the length on sediment transport and multiply sediment processes, sedimentation cycles. So thank you so much for your attention. And if you have any questions, I'm welcome here or in the chat.
Okay, so good afternoon, everyone. Firstly, I would like to apologize for my very bad voice conditions because I'm ill, but I will try to present you some results from the fluvial systems in Svalbard and also from Antarctica. Here are some brief information about me, about my research, and also about my work. Now I'm working in flood protection, river restoration, and some protection of inhabitants, but I studied the sediment transport in polar environments on Svalbard and also in Antarctica. We will move to these very nice polar regions to 3 catchments. 2 catchments will be located on Svalbard in Petunia Bay, and 1 catchment is in James Ross Island in Antarctica. The aims of the study are to describe the morphological characteristics which influence the sediment transport in these 3 selected catchments, and after that to analyze the downstream changes which occurs in the whole braid plane, and also to analyze the channel morphology and the very active channels due to whole areas. And after that, to explore some possible controlling factors of these changes. The main controlling factors are the sediment sources, connectivity in these catchments, and also the variable lithology. Here is the overview of 1 catchment. This is the Keller catchment from Antarctica, and you can see there the very active some very active channels, and on the other hand the inactive channels, which are flooded only due to high discharges. And why fluvial geomorphology in polar regions? If we want to observe some changes in the channel changes, channel bars, and its moving, we need to observe the hydrological cycle, and also which is connected to the meteorological conditions and to glacial melting. Here in polar regions, we have the natural environment without any people changes, without infrastructure, and we can see the bright changes in the braid plane. Also, here is no vegetation cover, which is for our geomorphologist or sedimentologist very good conditions, that the channel bars are not stabilized by vegetation. And also here in these catchments in polar regions, we have the very huge sediment supply, and we can observe there the connectivity, which is not influenced by the vegetation cover and also by the constructions of some people's work. If we have a look to the basic characteristics of these catchments, we can see the upper part of the catchments with some very huge and steep slopes, which are mostly covered by small glaciers or some snow patches, which also influence the sediment inputs to the active channels. Here is some part of upper reach. This is from Antarctica, and we can see also the hyaloclastite breccias, which is some remains of erosional processes, the huge boulders which were transported by glaciers in the past. Also, they appears in the middle reaches on some places and stabilize the channel bars. And on the other hand, in the lower reach, we have there a very wide braid plane with many active channels, which obviously transported many kind of material. Now we have a look to methods. My research were divided into several phases. In some preparation phases, it's a very important step before expeditions, because during the polar summer, we have only one chance to sample some sediments, sample your or select your localities. So you need to study orthophoto images, topographic maps, and history of each locality. Especially in Antarctica, this picture comes from the Keller catchment. We have the Mendel station and the possibility to go there to expeditions. Matěj, in the very first section of this geomorphological presentations today, also talked about this locality. We have there the station, and you have only one chance to select there your samples. Also, this is very important to check the weather forecast and everything, because these conditions are very, very changeable. At home or in the office, you also define the potential sediment sources and sediment sampling localities. On digital elevation models, you proceed slope analysis and many others. And also you study geological map, because you need to know the petrological types of the sediments, the petrological characteristics, and many erosional characteristics of these localities. After that, during the fieldwork, you proceed to geomorphological mapping. You sample sediments on selected localities, and you verify the sediment sources. After that, also you sample sediments. There can be many changeable fields, and after that, in a laboratory, you study the axis and degree of roundness, and also many other characteristics. Here at the Keller stream, we also did segmentation of the catchment of the active braid plane. We measure the channel width. We did a profile method, and also we counting the brinding index. In the sediment characteristics measurement, we define three main types of the petrotype which are transported by the Keller River, and also we determine the degree of roundness of each class. In the case of sediment connectivity, we study the sediment sources its type, the dynamics of the sediment source, and we proceed sediment connectivity map according to methods of Cavalli 2013. Here you can see the brief characteristics of the Keller catchment. Keller, this is the one from Antarctica, which is seen on the small map. And if you see the legend, we determine the three main type of the sediment sources. And one of the most important is the morainic sediment sources, which is the side moraine of the Whiskey Glacier. The other ones are debris flow dominated fans. They are very active slopes with a very high steep slopes. And one of the largest is the fluvial flow dominated fan. It's also very active because the side streams are fed by the glacier, by the Davis Dome ice cap. Here you can see the overview of the catchment. No vegetation, very coarse material on the sleeve, and there are some pictures from the river catchment. As I talked about the segmentation, we divided the main Keller River into 7 segments according to confinement index, the elevation, longitudinal slope, the processes which occurs in some segment. For example, the activity of site sediment sources, activity of main channels, and also the channel weight and the confinement index, as I said. And here you can see some brief characteristics which occurs here. In the case of channel width, here you can see that the channel width, the main channel, start brideing in after one kilometer, and here are very intensive changes, because at this part 1 to 8.
2 minutes, please. 2 minutes.
What? Yeah, 2 minutes. Okay, thank you very much. So that's the channel width. Here, brideing index. Here also you can see after the connection of sediment sources, there are many changes. There are sediment sampling localities in sediment sources and also in active channels. Here are characteristics connected to slope, just for your overview. And here is the sediment connectivity map. The highest connectivity is in the upper parts, and here in the central part, which the lakes are occurred, it's very low. Now lithology, but I would like to show you changes in the roundness and also the comparison with the localities in Svalbard. Here we have 2 catchments, the Munin Valley, which also here you can see the morainic sources, the fluvial flow dominated, the green one, and the colluvial, the debris flow dominated. Here are very active processes, and the sediment sources, especially the morainic ones, highly influence the sediment transport in a whole river. Here you can see the graphs, and I would like to point these graphs. Here you can see the very huge amount of very angular crust which comes from the morainic material, and after the transport is very intensive. This is the limestone and sandstone and pictures, but the last catchment I would like to talk about is the Herby River catchment. This is the catchment which is characterized by the 2 huge glaciers, the Herby and the Hell glacier, and also the huge braid plain, which here we can see another type of the sediment sources which influence the sediment transport. Here is also the huge transport time and the distance to the sea, to the end of the bay. Here are some pictures. On the top, you can see the Hellbrand and Helbebrand, the source localities, the frontal moraine, and the active braid plain, which are eskers, hummocky moraines, and many other sediment type sources located. Here, another picture of the influence of the petrological types in many sediment sources, and also the influence or the change in sediment roundness in this catchment. Here you can see the debris stripes, which are created by limestones, and they are very, very angular. So the huge amount of clasts which comes from these debris stripes is or occur in the whole sediment transport with some changes and some fluctuations. So that's that was only a few results from my work. We define the three dominant sediment type sources: debris flow dominated fens, fluvial flow, and morainic. The increased roundness is visible from the sediment transport, and also the point is that the fluvial material from localities which are closer to the main moraine, the main morainic system, has a shorter transport and is composed by very angular clast. So, and we can see in both catchments very fast changes during the higher discharges. I would like to thank you for your attention, and I would like to thank also my supervisor, Dan Nivot, my colleagues in the field, and also to Professor Surian from University in Padova, and Professor Cavalli for the helping with connectivity. So thank you very much, and if you have any questions, you can ask me.
Okay, thank you very much again. Good afternoon, everyone. My presentation focuses, as you can already see, on records of past high-energy marine inundation events. And of course, by high-energy marine inundation, the first thing that comes to mind is paleotsunamis. Many catastrophic tsunamis have affected coastal areas worldwide since antiquity. The map on the left shows the Euro-Mediterranean tsunami catalogue as a result of a systematic and detailed review. It shows the spatial distribution of the historic tsunamis occurred in the Mediterranean region. Now, if we compare this map with the bottom right one, we can easily associate these events with areas that display intense tectonic activity. The bottom right map shows the distribution of seismogenic faults, composed seismogenic sources, and active subduction zones. So it is pretty obvious that it is the tectonically active coastal areas, especially those in close proximity to tectonic plate boundaries and submarine active major faults, that are characterized as prone to tsunamis and increase the corresponding risk. Here we can see that Greece is very prone to tsunami activity. So let's move now to the first case study in Western Greece and see how such events can be recorded on the coastal sedimentary stratigraphy of the Livadi coastal plain, which is located at the northernmost part of the Gulf of Argostoli in Kefalonia Island. Kefalonia Island, as you can see, is located at the northwest edge of the Hellenic Arc in a tectonically and seismically highly active area. The tectonic situation here in the broader area of the Ionian Islands is highly complex because collision, subduction, transform forming, faulting, spreading mechanisms are all concentrated in a very small region. So now the study area, the coastal plain of Livadi, is a low-lying, swampy, marshy environment with a maximum elevation of 2.8 meters, and it is separated from the Gulf of Argostoli by a barrier beach. In order to obtain information about the late Holocene stratigraphy of the plain, 4 cores were collected from the back barrier beach swampy area of the plain using a portable vibratory corer coupled with geomorphological mapping of the broader plain area. The cores, which, as you can see on the table, extended to a maximum depth of 5 meters, were granulometrically and paleontologically analyzed in order to determine the depositional evolution and the paleoenvironmental history of the coastal plain. In total, 45 sediment samples were taken from selected layers at decimeter intervals. The chronostratigraphy was obtained through C14 AMS dating of selected samples. The fine sediments along the plain observed not only superficially during the geomorphological mapping, but also in the core samples are indicative of a coastal lagoon which has been enclosed by spits and bars as the plain has evolved during the Holocene. These figures depict the granulometric and paleontological analysis along depth for the 4 boreholes. I'm not going to get into details for those figures, but what is important to see is this figure, which summarizes the facies identification of the 4 boreholes, providing clear lithostratigraphic sequences. We distinguished 6 biosedimentary units, which in general are characterized by fining upward sequence, starting from a basal marine unit, which gradually gives its place to units representative of lower energy lagoonal depositional environments, covered on top by sediments of a unit which is dominated by terrestrial processes. These biosedimentary units are occasionally interrupted by high energy marine inundation layers, which are indicated in these figures by the red zigzag lines. In Unit A, which is the basal marine unit, the presence of angular and subangular terrigenous quartz grains, as well as a 2 centimeters thick pebble cluster horizon with numerous shell fragments in a sand matrix, are all evidence of a high energy event. Input of angular quartz and feldspar material is a common feature due to tsunami backwash. The age of this sequence has been determined through radiocarbon date of a marine bivalve preserved in the middle of this unit in L2 core, and yielded an age of 4,280 years before present. Since this shell was collected from the pebble cluster horizon, it can only provide a maximum age of this high energy event. The presence of a coquina layer within Unit P from core L2, which also contains mixed material from different environments, deep marine, shallow marine, coastline, and lagoonal, enhances again the hypothesis that the Levadi plain has been affected by the influence of high energy events. The presence of angular washed material, quartz and feldspars at the upper part of the brackish freshwater lagoonal Unit C, again possibly indicates a high energy marine inundation event. At this point, I would like to highlight that effectively discriminating storm from tsunami deposits is one of the most challenging topics in coastal geoscience. The storm versus tsunami debate is particularly strong in the Mediterranean, an area that is prone to both multi-site seismic activity and storm events. A study by Mariner in 2017, based on stratigraphic archives for the last 4,000 years, provides evidence for periodic cycles of 1,500 years, strongly correlated with climate deterioration of the Mediterranean and North Atlantic. And this, I think, challenges up to 90% of the original tsunami attributions and suggests that most of these events are better ascribed to periods of heightened storminess. In any case, the presence of sedimentary layers which contain terrigenous, angular and subangular washed material, quartz and feldspars indicate tsunami backwash with a relative certainty. For the remaining high energy marine inundation events in our study, the possibility of storms cannot be totally excluded. Now, let's move on to another case study to northern Greece at Alikes Lagoon, which is also a low-lying wetland of approximately 12 square kilometers with a maximum elevation of 1.3 meters. Alikes Lagoon is located at Cape Atherida at the western coast of Thermaikos Gulf. The broader study area lies in close proximity to the active tectonic structure of the North Aegean Trough, and of course the western propagation of the Anthemundas fault. So this study aimed, among others, to reconstruct the Holocene paleogeographic evolution of the Alikes lagoon and to detect possible high-energy marine inundation in events. So we followed pretty much the same methodological procedures with geomorphological mapping and drilling. In total, 64 sediment samples collected from 2 cores were granulometrically and paleontologically analyzed. Moreover, 2 shell samples were radiocarbon dated, providing the chronostratigraphy of the cores. The geomorphological mapping revealed a relatively wide field of vegetated, semi-stabilized sand dunes that has developed around the lagoon. These coastal dunes act as a physical barrier along the coast that prevent inland penetration of the sea waves and therefore allowing marshes to form landwards. Moreover, the eastern part of the lagoon consists of a series of beach ridges, signifying recent propagation to the east. 2 groups of beach ridges were recognized according to their orientation, their ridge and swale topography, changes in vegetation, and we saw that this orientation is in accordance with the shallow water circulation patterns of the western coast of Thermaikos Gulf. This figure again summarizes the granulometric results and the paleontological analysis results. I'm not going to get into detail, but what is worth mentioning in this figure is the layer indicated with a red rectangle at Al2 core, at the right part of the slide, from 268 down to 275 centimeters, where the granulometry suddenly changes to coarse sand with silt, containing also rip-up clasts and feldspar material. The sharp contact at the base of this layer documents an erosional surface, which indicates an abrupt change in the depositional environment, a high-energy marine inundation event. A fluctuation between brackish and marine environment was also marked by the paleontological analysis, but I will get back to this shortly. Both the sedimentological and faunal analysis showed us, allowed us to distinguish 4 bisedimentary units. The sedimentary record is generally characterized by a fanning upward sequence of autochthonous sediments, which is pretty common in lagoons. This sequence is marking the transition from an open shallow marine environment to a protected lagoonal of lower energy. And based on the radiocarbon dating of a shell from a depth of 440 centimeters, it is suggested that the establishment of the lagoon can be safely put around the 6th millennium BP. And the confinement of the lagoon, okay, thank you. The confinement of the lagoon can be attributed to the formation and evolution of the 2 groups of beach ridges that I showed you previously, one generating from the north and one from the south. The low energy unit B, the low energy lagoonal unit B, is intersected by a 7 centimeters thick layer from 275 to 268 centimeters of higher energy depositional conditions of allochthonous origin, as indicated by the microfauna and the presence of feldspar material, which is considered common due to tsunami backwash. A similar strong signal, marine signal in the same region, was also documented by Racherter et al. In a core located very close to Al2 core of our study, as well as at Cape Epanomi and Sozopoli, as you can see the map in the middle. The authors in their study describe a 50 centimeters thick layer of tsunamite, which correlates well with the high energy marine inundation layer documented in our study at the same depth. They also found a second layer, a high energy layer, at a depth of 200 meters, which has not been found in either 2 cores of our study. AMS dating of an intact shell right above this high energy layer suggests that the area has been impacted by tsunami not long before 4,330 years before present. And in an attempt to find the culprit of such an event, the North Aegean Trough is considered tectonically and seismically very active, and the westernmost segment of this fault of approximately 55 kilometers, which accommodates an horizontal as well as a vertical displacement, could generate a magnitude 7.1 seismic event, producing a maximum vertical offset of 4 meters. So this makes it a good candidate for tsunami hazard in the area. Thank you very much for your attention.
Thank you. Good afternoon again. My name is Anna Utkina. I'm a PhD student at the Institute of Geography of Russian Academy of Sciences. And today I would like to present our research concerning the Upper Volga's incision valleys and our recent data on their geomorphology, age, and development history. So first of all, a couple of words about the Volga River itself. It is the largest river in Europe. It flows through central and southern Russia into the Caspian Sea. Nowadays, it is almost entirely regulated. And as you can see on these pictures to the right, the river changes quite dramatically from upstream to downstream. So in our studies, we are focusing on the most upstream part of the river, which is called the Upper Volga. Although the Upper Volga has been the focus of extensive research, its origin and evolution remain mostly uncertain. Moreover, there are no reliable chronology available for its valley. Another important factor to say about this part of the valley is that it was heavily influenced by Pleistocene glaciations. On the map to the right, you can see two ice sheet extents present in the Upper Volga Basin. The first one is MIS6 ice sheet extent, and the second one is MIS2 ice sheet extent to the north. And one of the key issues of the paleogeography of the Upper Volga concerns the formation of incision valleys, since this process is associated with the river network restructuring. So the two incision valleys of the Upper Volga are located near the town of Tutaev here and the town of Plos here. So what are the incision valleys? These are narrow sections of the Upper Volga Valley characterized by a deeply cut channel and the absence of river terraces, as you can see here on the cross-cut sections. Their formation is assumed to involve a rapidly occurred cutting through the local watershed. Local watersheds here are end moraine ridges of MIS6 glaciation. So since such valley sections usually indicate the relatively young age of the valley, the researchers conclude that it joined the rest of the Volga River system only recently, supposedly in late Pleistocene. So most researchers argue that the formation of the Upper Volga River was largely affected by the last glaciation event during MIS2. And during that event, supposedly Upper Volga could have been one of the regions where preglacial lakes emerged. So one of the most popular models of the Upper Volga formation created in the 1970s by Kvasov suggests that the river itself did not exist prior to the LGM, last glacial maximum, and at that time the Upper Volga Basin was covered by a large lake system, showed here on this map by shaded area, that only disappeared around 14,000 years ago, after the incision valley near Plos was formed. This model does not mention the Tutaev incision valley mechanism on formation in particular, but the author claims that the valley also formed a little bit earlier to the Plos one, around 15,000 years ago. So the main problem with this model is that it lacks proper stratigraphical and geochronological evidence, so it needs to be tested. And another important factor that could not have been considered by Kvasov in the 1970s is the glacial zetetic adjustment, or GIA, influence on the Upper Volga Basin. So the main point here is that during the last glacial maximum, and during the deglaciation, a glacial forebulge, the uplift of the lithosphere, must have formed somewhere in the upper Volga basin. It was suggested in the 90s, as you can see here, and also it is confirmed by modern glacial isostatic models. For example, as shown here, I6G model by Peltier. The glacial forebulge should have been located in the upper Volga basin. So supposedly it must have skewed the basin to the north in the direction to the ice sheet, and possibly created a dam for water, and that would have been the mechanism or formation of preglacial lakes. But this hypothesis needs to be tested, and in order to resolve the main problem with the upper Volga, namely when and how was it formed and when it joined the Volga River system, we focus on the reconstruction of the incision valley formation history. We study the geological, geomorphological structure, we establish the age, and we test the hypothesis of the preglacial lakes formation. So we have three main study sites, the one near Tutaev, the one near Plos, and the one 30 kilometers upstream from Plos. So the first site located near Tutaev incision valley, we studied the left side of the valley here that, according to previous reports, had a series of probable river terraces. So we made 5 boreholes, and we studied also one section, and our field studies allowed us to locate the Holocene river terrace of the upper Volga, presented here. As you can see here, it was dated by using luminescence dating techniques, and we confirmed its Holocene age that way. All the other 5 boreholes display no alluvial or limnic sediment. They display mostly MIS6 steel, shown here by pinkish tone, and slope sediments dating back to MIS2 mostly. And also we were able to locate probably fluvio-glacial sediment, shown by greenish tone here. And as you can see, it is dated by IRSL dating to be around 200 and even 300,000 years old. But as of now, we're not certain whether these ages overestimate because of poor bleaching or whether they are accurate. And this is not the only site with such ages in the upper Volga Valley. Moving on to site 2. That is located 30 kilometers upstream from Plos incision valley. We also studied this site because according to previous reports, there were some river terraces to be found, and we located 2 terrace-like platforms here. The lowermost one, around 100 meters, shows us the Aeolian sequence, Aeolian sediment sequence that dates back to the last deglaciation and lies on top of MIS6, presumably MIS6 steel. But the uppermost terrace, as you can see here, is also highlighted by the same greenish color, and luminescence dates ages that we obtained also show really old ages. Again, for now we cannot say whether these ages are accurate or whether they are overestimates. So further research is needed for us to resolve this contradiction. Finally, moving on to the site 3, located in the Plos incision valley itself. Here, according to the previous research, and according to the definition of incision valley, no river terraces were supposed to be present at all, no alluvial sediment, but we were able to locate a remnant of a river terrace on the left side of the valley here, almost directly across from Plos. And here we studied a 15-meter deep sediment sequence, and also dated it using luminescence dating. And here we can see the results, the ages. and they all correspond mostly to late MIS6 and MIS5, except for this middle one. That is some kind of mistake, so we do not consider it further. So this site, this terrace virtually confirms that the Upper Volga did exist. The Upper Volga Valley did exist before MIS2, and supposedly it was formed during late MIS6. So this site only contradicts the whole previous class of theory that I talked about in the beginning of my talk. And finally, moving on to the GIA modeling results, we employed a freely distributed online software, Selen version 4, that allows to study the changes in topography under the GIA influence. We studied these changes for 3 time periods for the LGM and 2 time periods during the deglaciation. And for visual demonstration of these changes in topography, they created river profiles for each of the time slices. So this is the river profile of the Upper Volga from its source to the left to Plos to the right. And as you can see here, no major skewing of the basin topography is observed towards the glacier, which was located somewhere around here. Okay, thank you. And the only thing that we can see is that the glacial forebulge apparently was located in the section of the valley from Rybinsk to Plos. It lifted up the profile a little bit, and throughout the deglaciation, possibly it caused notable change in elevation of the Volga riverbed and caused therefore a cutting episode in the river. So moving on to the conclusions, most likely both incision valleys were formed in the MIS6, and one possible mechanism of their formation that we can imagine is that it happened during the formation of a glacial meltwater runoff system connected to the retreat of MIS6 glacier. So no MIS2 limnic or alluvial sediment were found in the valley, and GIA modeling did not show any proof of possible lake formation due to the skew towards the glacier. We also found proof of the early Holocene accumulation in the valley, in the two-type incision valley, and thus we conclude that most likely the general configuration of the Upper Volga Valley was established already in the late MIS6. So the previous model is possibly wrong, and during MIS2, the river and its basin were already existing. Thank you very much for your attention and for giving me opportunity to present my research here today. I would welcome any questions that you have.
Good afternoon. My name is Aleksandra Osika. I'm a PhD candidate at the University of Silesia in Katowice in Poland. And in my presentation, I will say a few words about what we know about the Holocene history of Hornsund in southern Svalbard. So Hornsund is the southernmost fjord along the west coast of Svalbard. It is known for numerous glaciers, and the great majority of them terminates in the sea. And also the north coast of Hornsund is the location of the year-round Polish Polar Station. The most interesting part of the study area is the head of the fjord, where we have 2 tailwater glaciers, Hornbren and Hambergbren. Where we have 2 tailwater glaciers, Hornbren and Hambergbren. So these glaciers form an ice bridge which separates the Greenland Sea and the Barents Sea, and the warmer water masses carried by the West Spitsbergen current from the colder water masses carried by the East Spitsbergen current. So in general, the fluctuations of glaciers in Hornsund in the 20th and 21st century are quite well studied, and also the Holocene paleogeography of Svalbard is getting more and more attention. But the studies on the southern part of the archipelago are still sparse. So the aim of the study is to reconstruct the fluctuations of glaciers in Hornsund in the Holocene. As we deal mainly with tidewater glaciers, as a source of data, we can use, for example, the subfossil mollusk shells, which were collected in several ground moraines and lateral moraines of selected glaciers. So the results of radiocarbon dating indicate the periods of the glacier retreat and the existence of marine environment in recently glaciarized areas. And here, for example, you can see the ground moraine of Hansbren on Baranovski Peninsula, and on the right you can see the ground moraine of Hornbren on the Tereskeren Peninsula, and the latter with distinct, also obliterate crevasse squeeze ridges after the surge of Hornbren at the end of the Little Ice Age, so at the end of the 19th century. Here you can see the examples of the shells which were collected from these ground moraines. These species are not thermophilic. Nowadays they are also living in Svalbard, but as a suspension feeding species, they prefer the central and the outer part of the fjords because they are very sensitive to high amounts of inorganic material, and they are not found near the ice cliffs, as the high amount of inorganic material would clog the refiltering apparatus. And on the left you can see also the examples of mollusk shells. These were collected from the forefield of Hornbren, which is a surging glacier, and here we can see the relationship between the size of the fragments and the distance from the glacier terminus, as the biggest shells were collected from the site where they have been redeposited during the Little Ice Age, and the smallest ones have been obliterated and damaged several times during subsequent surges on a smaller scale. Here you can see the compilation of the radiocarbon dates. These are the median calibrated ages of mollusk shells from the glacial sediments. So these are the light blue ones. Mollusk shells from the raised marine terraces. These are the dark blue ones. Organic material which was collected within the moraines. These are the green ones, and also sediments melted on the surface of Hansbren. And this is the compilation both of previously published dates and of new data. So one of the most studied glaciers in Svalbard and also in Hornsund and also in Svalbard is Hansbren. This glacier is close to the Polish Polar Station, and here you can see the extent of this glacier and the end of the Little Ice Age, so at the end of the 19th century. In this picture on the right, you can see the extent of the glacier in 1936. So as you can see, the sites where the mollusk shells were collected were covered with ice during the Little Ice Age. And in this compilation, you can see that the mollusk shells and also sediments indicate the glacier retreat in the early and in the middle Holocene. The oldest sample indicate the glacier retreat before 11,200 years BP, so very early. But this is in line with the results from the other regions of Svalbard, where the glacier is also retreated in the early Holocene. And in general, the early and middle Holocene was the period where the climate of Svalbard was much warmer than at present, and the glaciers have reached their minimum extents. In general, many tidewater glaciers even retreated onto land in this period. So here you can see several study sites where the mollusk shells were collected. The letter A is the ground moraine of the Baranovski Peninsula. The letter B is the ground moraine at the foot of Fanetoppen, so at the foot of this mountain. And we also managed to collect sediments and also mollusk shells, even from an iceberg which cracked directly from the bottom of the glacier. And also these results indicate the existence of marine environment in this area about 10,200 years BP. So moving to the head of the fjord, here we have two tidewater glaciers, Hornbren and Hambergren. And the results of the GPR surveys published by Gravitz and others indicate the existence of a subglacial depression below this ice bridge. So in the next 20 years, we will witness the opening of Hornsson Strait and separation of Sorkabrand, so this area, from the rest part of Spitsbergen. And here on the left, you can see the approximate course of the shoreline and also the approximate course of the isolines, which indicate the depth of the bottom of the glacier. So in 1936, the extent of these glaciers were much greater than present. And also in general, during the Little Ice Age, Hornbren advanced further to the west in Hornsund. It partially overpassed Träskelen, so this peninsula, and Hamburg-Bren extended much further to the Barents Sea. Here you can see another compilation. This is the compilation of the median values of radiocarbon dates of mollusk shells, which were collected in the forefield of Hornbren. And as you can see, we have the radiocarbon dates from the early, from the middle, but also from the late Holocene. And these results also indicates the period of the glacier retreat and which resulted in opening of the Hornsson Strait in the past. And the oldest mollusk shell from Träskelen indicate the existence of the Hornsson Strait at least 10,000 since 10,900 years BP or much earlier. As you can see, there is a gap in radiocarbon dates between 3,900 and 1,300 years BP. This corresponds well with the period of cooling in Svalbard, the so-called neoglacial, when the glaciers of Svalbard advanced. So as a consequence, the Hornsund must have been closed and functioning as a fjord. This is in line with the previously published results of beryllium dating from Träskelen, which indicate two glacier advances. The first one was around 1,900 years ago, and the second one about 700 years ago. The youngest radiocarbon dates from Träskelen indicate the glacier retreat around 1,300 years BP. It also corresponds well with the so-called little climatic optimum, which was the period of the glacier retreat in Svalbard. As you can see in this picture, nowadays the strait is closed since the Little Ice Age, when the glaciers advanced and reached their maximum known extent in the Holocene. So here you can see some pictures from the field. These are the pictures from Träskelen. So as you can see, in 1936, Träskelen was partially covered with the glacier, and it was partially overridden by the glacier, which extended further to the west during the Little Ice Age. And nowadays we can see the hummocky terrain with degraded crevasse squeeze ridges after the glacier surge at the end of the 19th century, so at the culmination of the Little Ice Age. And moving to the southern coast of Hornbukta, so the second study site, in 1936 it was of course covered with ice, and nowadays we can also see the crevasse squeeze ridges. And as you can see, the layer of diamicton is quite thick, as you can see in this erosional incision. So to sum up, the fluctuations of glaciers in Hornsund occurred synchronically with other regions of Svalbard. We had the glacier retreat in the early and middle Holocene, especially during the so-called Holocene climatic optimum. Then it was followed by the glacier advance in neoglacial. It was after the 4,000 years BP. It was followed by the glacier retreat during the medieval warm period between 1,300 and 700 years BP. And we had the glacial advance during the Little Ice Age with a culmination around at the end of the 19th century. And nowadays we observe the glacial retreat. And here you can see the sound probability density of radiocarbon dates of mollusk shells, which were collected just in the forefield of Hornbrann, because in general, the fluctuations of Hornbrann and Hamburgbrann have been determining the functioning of Hornsund as a fjord or a strait. So here you can see the periods when Hornsund was functioning as a strait. So it was the early and the middle Holocene, and also the medieval warm period, but here we would like to have more data about it. And also here we can see that Hornsund was functioning as a fjord in Neoglacial and during the Little Ice Age. And of course, so in general, in the periods of the glacial retreat, Hornsund was functioning as a strait, and in the periods of the glacial advance, Hornsund was functioning as a fjord. So if you are interested in this topic, you will have the opportunity to read more about the Hornbrann-Hamburgbrann system in our paper, which is now in press. So thank you very much.
Good evening, dear colleagues. I'd like to present my topic. I'm Daryl Bachov from a PhD student from Moscow Lomonosov State University, and my topic is about bionodes of the Northern Caspian lowland as a key to the Caspian Sea paleogeography. What do we name bionodes and how do they look like and where we may find them? It's a special, unusual giant dunes named after a member of the Russian Geographical Society, Karl von Baer, who described them first, who described their mathematical and morphological characteristics and their region. So the study of these landforms dates back to more than 150 years. And bionodes are a complex of elongated ridges and depressions, often close to
Daria, excuse me, you just have to click each slide on your left part of the screen so that we can see them. Now we are with the slide number 3. We haven't seen number 2, so if you can perhaps show us number 2 and then go on.
Here you may see the second slide. Do you see it?
This is number 3. Oh, this is number 2. Yeah, thank you.
Yeah, number 2. Okay, so bionodes are a complex of elongated ridges and depressions, often close to the sublatitudinal orientation, sometimes spatially asymmetric, that are scattered in the entire Northern Caspian region up to 0 meters above sea level. That is the upper limit of the later Hvalinian Caspian Sea transgression. So the red lines show this on the map on the left part. On the right, you may see a photo of bionodes landscapes in landscape in the real nature. So the main question of this discussion is then how and in which environments these forms appeared. So here's a geomorphological map of the lower Volga territory with different types of geomorphological landscapes. As you may guess, nodes have various morphology and mathematical characteristics. It's easy to identify them on a satellite image on the southern area in the Volga Delta as well as in the Ural Delta, but it's not the initial dune landscape because of erosional processes of these rivers and because of Novocaspian transgression influence. To the north, like Black Crab, you may see major linear bionodes by giant dunes with height up to 10-15 meters and length up to a kilometer in general. And the northernmost ranges are characterized by a nonlinear shape up to 5 meters maximum in the height. So where did we work? In general, our field work was carried out.
But we still see slide number 2. So don't forget to click each slide consecutively as you present. So otherwise, we won't see them. Yep. Okay.
So here you may see the fourth slide.
Number 4, yes, we do.
Yeah, and this was previous one.
Yes.
Sorry, I forgot.
So just don't forget, please.
Yes, okay. So in general, our field work was carried out in the northern Pre-Caspian lowland, especially in the Volga Delta region, and the geological map of which you may see on the right, were Holocene alluvial marine deposits with remnants of biennials deposits. So talking about inner structure of these giant dunes, there were 3 main lithofaces that we identified basically on sedimentary structures: visual characteristics, color, lamination type, grain size, and geochemical composition as a result of VDXRF analysis. In this day, biennials consist of 2 lithological formations based on early Hvalinian sediments named chocolate clays. From the top to the bottom of several outcrops, we may define lithophase 1, presented by cross-laminated very fine sand with lances of coarse sand with a very rare detritus. Then lithophase 2, it's a red color, which consists of cross-laminated very fine sand with thin layers of silt and clay pellets. At the basement, large mollusk shells are presented. And the lithophase 3, it is chocolate clays. We named them this way because of color and structure, because they're really like a chocolate. And this lithophase is composed of 1 to 2 meters thick, dominated by brown to dark brown clays with thin lenses of yellow-gray, very fine or fine sands. And low-angle cross-lamination of sand and clay with thickness about 50 centimeters are presented in the upper part of sediments. Sand layers usually contain shell fragments and wall shell species. Here you may see a typical null sediments lamination types like crisscross, diagonal, and interlying with horizontal ones. Lithophase 1 and 2 are often divided by erosional contacts where denudation occurred. I'd like to emphasize the unusual granulometric composition of the main lithophase 2. It's a main strata of the null, where about 30 to 60% of silt simultaneously with clay about 40 to 60% and the sand at most 25%. While topmost lithophases has high content of sand up to 55%, that means more dynamic environments than in lower layers. Several words about specific fabric features. Here we see some instance. So sometimes very beautiful ripple marks are found in sediments that are more typical to the water environments, and some crustaceans, perturbations of phenomorph were discovered in outcrops. That means a brackish water lagoonal shallow environments. Detritus lenses are also usual for lithophase 2, while wall mollusk shells are quite rare. 7 mollusk species like Didacna Pratak and others were identified from investigated null sediments that represent fresh water and brackish water environments. In the upper part of chocolate clays, brackish water assemblages were explored. Large and thick shells of Didacna Pratak and Parallel indicate long-term optimal living conditions with 8 up to 13 ppm paleosalinity of a basin. However, the abundance of shells Ceneris in the sand interlace could indicate a regular supply of fresh water and a decrease in paleosalinity down to 3 ppm. In contact between chocolate clays and lithophase 2, rich detritus layers and rare small shells could indicate an increase of current flows with suspended material and flow water environmental conditions. So we used mollusk shells to determine the radiocarbon age of a biennial, and the obtained dates show the age of a strata contacts between these huge stratus in giant dunes. The dates we obtained for chocolate clay, so lithophacid 3, correspond to the interval about 16 to 15 calibrated kiloyears. They correlate with the onset of the early Dryas cold stage. Dates for lithophacid 2 are varying between 14 and up to 13.8 calibrated kiloyears. It correlates with the beginning of a late Dryas cold event. And according to our data, biennials lithophacid are not younger than 11 kiloyears calibrated. And we propose that biennials as landforms could have been formed during the late Holocene and early Holocene transition. And the results are generally correlating with the period of deglaciation epoch after LGM. To sum up, the biennials are really giant dunes. The geological and climatic conditions of the epoch of their origin and evolution were unique. At present, analogous landforms close to the biennials in the northern Caspian region are not forming. However, there are several analogous landforms like giant dunes in Altai Mountains and others like giant dunes in Scabland area in Washington state. So regarding to the genesis, there are still many opinions, but most of them don't explain the problem of the formation of these landforms entirely. In our opinion, sedimentological features of biennial sediments are characteristic to the subaqueous environments of cool brackish water basin like a lagoon, with a weak subcritical flux on the bottom of which this dune appeared. Simultaneously, with the accumulation of sandy material and interlace of redeposit shells, background precipitation of clay fraction occurred. And the main takeaway message of our hypothesis is that the analyzed literature and field material preliminary allow us to conclude that these giant nodes are landforms that probably appeared at the end of Holocene time. It's late Neopleistocene, early Holocene. Then a water flow through the Manish Strait into the Black Sea. So that's all I wanted to tell you. Thank you for your attention, and I'm ready to answer the questions.
I understand that this is the end of the session. We don't have any other presenters. I'm going through the list of participants, but no one else seems to be present. So thank you very much to all the three speakers for this very different but each very interesting talk. And I hand it over to Mihai. So thanks a lot.
Thank you also very much, Piotr. And actually, we had a long day, but which went well. We had a lot of discussions on a lot of topics which were all complementary up to a point, and personally I really much enjoyed. I enjoyed the quality, the high quality of the work, and also I was very happy to see that each session was well in time, so we were able to keep up with the schedule. We would like to thank you all, the participants, very much. As you know, the session was recorded, right, Konstantinos?
Exactly.
And most likely, as it happened with the previous, the second edition, the one of last year, this as well will be posted on the website of the IAG. We would like to ask you to keep an eye on our website, since always there will be news concerning such events. There is a whole week ahead of us, which is dedicated to geomorphology. And there are so many actions which are dedicated to young researchers, to young geomorphologists. Again, I would like to thank you all very much. Konstantinos, the floor is yours for the final thanks, and then Mauro, if there would be something else that you would like to say, we have finished with our session, and thank you very much, all of you.
I have nothing to say, so I think Mauro must close the session.
Thank you. Thank you very much. So if I have to do it officially, let's change the background. Okay, so it's some advertisement of the IEG, if you let me do that. So thanks very much to the speakers for their very interesting presentation, for the organization of the webinar, which was also perfect, and also for the management of the webinar by the chairs, which was really perfect too. So I am very happy about the start of the International Geomorphology Week with these two events that took place today, the Africa webinar and the Central and Eastern Europe one. And the third one will be tomorrow. Actually, we will have more than one tomorrow. So we will have North America tomorrow starting at 6 p.m. Central European time, and then actually in the night for Central European time it would be 1 in the morning of the day after, the Eastern and Southeastern Asia and Oceania webinar. But you can find all the information on the IG website and at the link that was delivered this morning. So thanks again to all of you for this wonderful webinar.